Good morning. Distinguished guests, respected chair and co-chair, esteemed speakers, scientists from all over the globe, and researchers, industry professionals, and colleagues. After an intellectually stimulating session in the morning, and with thought-provoking plenary lectures yesterday and again this morning, we come together once more with renewed curiosity and purpose. Each session so far has added a new dimension to our understanding of the Earth's dynamic systems, and it is in this spirit that we continue our exploration, that we move forward in our morning technical session, Geohazards Decoded, Research for a Safer Tomorrow. Why is this echoing so much? Okay, anyways. This session brings together cutting-edge research, advanced methodologies, and emerging perspectives, all aimed at understanding natural hazards and safeguarding vulnerable landscapes and communities. So before we begin, it is my privilege to extend a warm welcome to our chair, Shri Pradeep Singh, DDG, NMH3, GSI, whose leadership in national geoscientific missions continues to guide critical research initiatives across the country. And I'm equally privileged to welcome Shri P.K. Singh, sir, DDG Mission 3 from GSI, Kolkata. May I also introduce our rapporteur for this session, Shri Gargi Chakraborty, who is Superintending Geologist, GSI CHQ, Kolkata. And we begin this morning with our keynote lecture delivered by Dr. Mauro Rossi, Research Director at the Institute for Geohydrological Protection under the Italian National Research Council. Dr. Rossi's internationally recognized body of work spans multi-scale modeling and of geohydrological processes, AI-driven susceptibility and hazard zonation, use of Earth observation data for process mapping, climatic data cube analysis, and development of territorial early warning systems. His contributions to open source modeling frameworks have profoundly influenced global geohazard research and risk mitigation strategies. Today, he will deliver the keynote address of this session, a framework for territorial landslide early warning systems. Dr. Rossi, the stage is yours.
Is the first one?
Yes.
Okay. Good morning, everyone. Can you hear me? Perfect. Okay. So thank you for the introduction. Okay, perfect. Thank you, sir. So thank you. Today I'm going to talk on a framework for the territorial landslide early warning system. Clearly, this is not a work just of me, but even it's a working. There is a working group which is developing these systems. Let's first start introducing what is a territorial warning system, which primary aims is the issuing of warning over a territory rather than a single site. And commonly, this is the duty of civil protection authorities or other national and regional administrations. Specifically, a territorial landslide early warning systems focus on the prediction and forecast of landslide processes over large areas and the issuing of the related warnings. Almost 2 decades ago, civil protection authorities of Italy asked our institute, which is called CNR-IRPI, to develop such a system for the entire Italian territory. If we consider one of the many landslide classification schemas, we immediately realized that there are different characteristics to distinguish between different landslide types based on the type of material, the type of movement, the type of the moisture content. This basically makes this single word, which is landslides, really underlining a series of heterogeneous processes. And this makes it difficult, if not impossible, to have a single forecasting approaches for all these heterogeneous processes. Whenever we consider the scales of forecastings, the spatial and temporal scales, we should consider that there is a variation of landslide processes through these scales. If we consider the spatial scales, we may go from the prediction of single landslide movement versus the prediction of multiple or populations of landslides. Whenever we consider the temporal scales, we may be interested in forecasting fast-moving landslides or slow-moving landslides, which actually correspond to different types of landslide processes. In the literature, there were many different kinds of forecasting approaches developed. We can barely classify these in geotechnical monitoring, physically based model, conceptual, and empirically based models. Not all these approaches work at all the scales. The territorial and the data demand and the data scales is basically increasing downwards. Our systems, which pretends to be territorial landslide early warning systems, works at these scales. Another important distinction we need to be is between the local landslide early warning system and territorial landslide warning system, looking at the forecasting approach. Whenever we want to focus on the prediction of single landslides or on what happens in single e-slopes, we are more using the geotechnical monitoring approach. We basically based our forecast on the monitoring of landslide features that could be kinematic features like velocity, acceleration. Whenever we are considering a territorial landslide warning systems, we cannot use such kinematic or such specific landslide parameters. Then we need to rely our forecasting approach on the use of a trigger. This is why to predict rainfall trigger landslides we use and we observe and we analyze rainfall as the trigger. These slides summarize a bit the efforts that we have done over the last 2 decades in Italy to develop such framework for the rainfall-induced territorial landslide early warning system. We started to develop a national landslide early warning system for the entire territory and for the entire railway network. Then we went towards regionalizations of these systems, and we developed specific regional early warning systems. Finally, this last period, we are developing what we can call impact-based landslide early warning system, which are mostly focusing on evaluation of the possible landslide occurrence over a specific exposure, in this case, a specific line, a specific part of the line of the railway network. But finally, I want to stress that in the last decade, starting from 2017, under a project which was called LandSlip, which was funded by UK NERC, we were starting designing a prototype systems a prototype territorial landslide early warning system working in India together with the GSI colleagues. And actually, under this new memorandum of understanding between GSI and our institute, we pretend to operationalize these systems. There are some key concepts on these systems that I want to show you. First, our system have the primary aims to forecast landslide processes with a trigger mechanism which is directly related to rainfall. This is an important distinction we need to do because it bounds the kind of and the amount of processes that we are able to predict. Thank you. We can simplify and say that these systems are based on the comparison of rainfall data and landslide rainfall thresholds. But actually, those systems are a bit more complex. And then they actually gives you a probability of a landslide occurrence. Those systems are able to restitute in output different kind of products. You have nowcast, landslide nowcast, which are forecasts of landslides using measures. We'll see that later. And proper forecasts, which are directly using deterministic or ensemble rainfall forecasts in input. And these systems produce hourly different kind of products. We do have a way to account the local propensity of a territory to have landslides, and this is done using a landslide susceptibility zonation or model. There is a cornerstone in this that is basically used by these systems, which we call the non-exceedance landslide probability. Basically, there is a model that for every couple of rainfall conditions, the rainfall cumulative and the rainfall duration, is able to restitute in output a non-exceedance probability over the possible landslide occurrence. This model basically relies upon or takes its scientific foundation on the landslide rainfall threshold modeling approach, which is a largely used model in the scientific literature. So we do have many evidences in the literature that this model has a robust scientific foundation. These models need to be calibrated using spatial and temporal data on landslide occurrence over the territory and on the corresponding triggering information, that means rainfall. Basically, for each couple of rainfall cumulative and rainfall information, here we have 4 dots for 4 possible rainfall conditions, the model is able to restitute this non-exceedance probability. Okay? This is, for any couple of values, you may get one single value non-exceedance probability, but then you may also have multiple values. This is why, in the past, we were developing different algorithms which were taking different values of the non-exceedance probability, and they were averaging, taking the worst condition, or more recently, taking all the possible ensemble conditions and deriving some statistical figures. And this algorithm, this is largely used in the last versions of our system, is called ensemble non-exceedance probability model, ensemble NEP or ENEP. But with all this information, which kind of products, forecast products, is the system able to restitute in output? Okay, let's suppose that we are at a given calculation time, and we may have information on the past rainfall history using, for instance, radar measurements or rain gauge network information. And with this information, that again are from the past, we are able to produce what we call the landslide nowcast, which pretends to give information on the possible landslide occurrence over the next 3 to 6 hours. But we can use even proper rainfall forecast models, ensemble, deterministic, and with this information, we are able to produce a proper landslide forecast. In our system, we are even mixing those 2 information to produce what we call combined forecasts. The system works at different spatial granularities. We started working at the rain gauge level, so basically information on the landslide occurrence was given at gauge locations. But then we are able to even produce landslide and nowcast and forecast over territory subdivisions. In this case, you see a subdivision that we call alert zone subdivision, which is a subdivision used by the civil protection for civil protection purposes mostly, and even for warning issuing. And then there are different versions of the products which are gridded or interpolated, basically raster-based products. Until now, I just told you how to calculate a probability of possible landslide occurrence using the trigger. We are not considering local landslide conditioning factors. This is done, again, using a susceptibility model. We basically take this information coming from the application of this non-exceedance probability model, and we multiply by the susceptibility. This is a sort of a filter. Whenever you have a rainfall condition which is probable to lead a landslides, and this is in non-susceptible areas, this is filtered out by this model. Clearly, there is a huge importance on the methods used to derive landslide susceptibility models. We were using different models in the past. We started from that one on the left, which was derived at using some sort of administrative boundaries. But now we have a pixel-based model, which you see on the right. But the most important part here is that you should know exactly which are the limitations of your models, including information on the possible performances in terms of calibration and validation, and even you need to know exactly which are the uncertainty associated to these models. And this is doable using error maps, uncertainty maps, and using different statistical metrics, and clearly doing different validation exercises. We do have, as I told you, a version of the system which is working all over the entire railway network of Italy. We basically overlap the information that are coming from the territorial landslide warning system with information on the landslide exposure along the railway network. This exposure information was calculated using different diversified modeling types, including mainly different types of landslide faults, flows, and slides. And those models were derived actually on the proximity of the network. These systems are able to restitute every hour a multitude of products. You do have many different kind of outputs. It's really fundamental for the user to have dedicated interfaces to look at the main forecast, but even to analyze of the possible products. This is why we distinguish always between two interfaces, the monitoring one and the analysis one. The monitoring one is the monitoring interface that should be on the screens of civil protection centers, but then the user should be able to take each single product and analyze them in space and time. And this is done using this analysis product. Here I've just shown some of the systems we are developing. You see how these interfaces appear. One important thing is that we are able, even for the same systems, to develop more interfaces. Particularly, the monitoring interfaces can be customized depending on the scientific and technical user needs. That's important. Here, I'm just showing you how this impact-based system works. You basically have only an exposure. Here you have these green lines that are basically two railway network lines. And the system is able to account specifically the forecast along these line tracks. When you go to operational landslide forecasting, it's fundamental to have even some sort of approaches for the hardware and software. This is why in these 2 decades we learn how much important is having dedicated landslide, dedicated labs hardware infrastructures. And it's important all these activities which are able to redundate pieces of this hardware. Our systems basically are developed using open source softwares, all, and they are basically virtualized. This makes possible to transfer easily those systems on the cloud. There are complications actually, but this is not because the software. Until now we just discussed how to prepare a proper landslide forecast, but we didn't discuss how to reach the warning. This is a key part of these systems. Before we were sort of describing the early forecasting part, not the early warning part. And this is probably the most open problem which is in the literature. Actually, we develop a methodology to pass from the forecast to the warning. We first benefit of the richness of products that the systems have, and we select several products. For each of these products, we need to decide some thresholds. And then we do have a rule engines which is able to compare products and thresholds to reach what we call landslide forecasting scenarios. Okay? And this is done not considering the specific user needs. This is simple a forecast, a landslide forecast. Then we do have the opportunity to associate warning levels to the different forecasting scenarios, and then to have the corresponding actions. This is normally done through a standard operative procedure, an SOP, and this part, the previous part, the left part, is normally under the responsibility of forecasters, while the left part, the warning and the action part, it's under the direct responsibility of institutions and end users of the systems. And normally, whenever you construct or you build these systems, the interactions between the two, it's limited to the warning level and forecasting scenario association. But it's fundamental, as we discover, to have an interaction which is much larger, starting from the forecasting side. Landslide and warning system evaluation is key. Is a key information we need to provide. And validating a system doesn't mean only to validate or to check how much good is the prediction of the system, which is called forecasting capabilities. But it's even important to evaluate which is the operational efficiency of the systems. If we promised to produce 24 forecasts a day, are we able to produce this? This is not an easy question to answer, and you do need to have dedicated procedures for doing that. In particular, for the forecast capability evaluation, it's important to have dedicated data collection activities, and we design even interfaces and data structures to contain all this information, which can be used regularly on demand to evaluate the system performances. The operational efficiency instead is mostly done through logging and checking. It's a sort of a proceduralized work to do this. Okay, clearly we have learned a lot of lessons in these 2 decades. First, the theory is different from the practice. Every single landslide paper finished saying something about early warning, but no one knows how to do this. So those are complex tools, and the implementation, running, and maintenance is difficult. So it needs dedicated competencies and funding and a continuous support. That is fundamental. And those are not only scientific. There is a huge advantage on using multiple forecasting approaches. Ensembling forecasting approaches will be the best. Those systems must be continuously evaluated. If you want to start this journey, you need to understand immediately the importance of this information. There is the need of system users and forecasters to interact continuously. This is fundamental, to let the end user understand exactly what a product means to take proper decisions. Those systems are, I say, live. That means that are evolving in time. Those systems are in the cutting edge between science and innovation. This is important, no? You don't have consolidated systems, no? You don't have the Office suite, and you resolve bugs, no? Using millions of exercises. Here, you need to build continuously. There are future challenges as well. Clearly, there is the need to fill this gap between the translated forecast warning. This is still an open question. We pretend to have a solution, but clearly this is one of the possible solutions, and we don't pretend to have the right one. We have one. We need to find a balance between the unavoidable landslide early warning system complexity and the easy-to-use demand from the end user. Whenever you ask the first time to end user what wants to have from a landslide warning system, the question is easy. I want to know exactly when a landslide will happen and where. No, this is not possible, clearly, no? The first answer that we give. So there is the need to try to go in that direction, but accounting all the limitations of the modeling approaches that we are using. Clearly, there is the need to understand which should be the appropriate accuracy, depending on the landslide early warning scale. This is something that basically has a lot of possible ways to follow. And clearly there are many others that we don't know. Okay, thank you. If you have questions.
Thank you so much. Because we are running short of time, so we will allow questions. Thanks. Questions? Yes, please.
Sir, the model which you have shown basically shows a very high, a good amount of the rain gauge parameters. And we especially if we talk of the in Indian context, we don't have that much of rain gauge stations. So for how long one particular rain gauge station is valid for, what will be its resolution? For example, if I have a very large area and I have only one station over there, will it be valid for the whole region or like that? Or it has to be further subdivided on the basis of some kind of the slope or like that?
Okay. Thank you. This reminds me some discussion I already have with the colleagues, but this is always an important question to answer. Okay, first, we know you do have a loose rain gauge network. This is why in the systems we were developing here, we are mostly using forecast, landslide forecast, which cover entirely the territory. That's the first part. The second part is that the spatial representativeness of rain gauges, which sent us go to the direction of the rainfall spatialization approaches. Normally, you don't have a given distance. You have a context. It depends on the context where the rain gauges is installed. If installed in a hill slope, suppose that you have two close rain gauges. One is in this side of the hill slope, the other is in the other side. In the morphological condition and specific climatic condition you have here, probably those two gauges are closer, but they are giving really different measures. Maybe it's better having a rain gauges which is on the full slope, even more far from this one, and this will be much more related to this. So basically, this depends almost on the local conditions, and in particular on the local topographical conditions, but even on the climatic settings, because sometimes those weather conditions which are able to trigger landslides mostly have predefined patterns. Whenever you have monsoon seasons here, you do have a given directions where this rainfall events follows, approaching the territory. And this may tell you something on which is the representativeness. So it's not an easy question. It's much more complex than that. Thank you for the question.
Thank you very much for the very interesting presentation here. So a question I had was regarding the validation, right? So you have a event, and how do you actually validate it, in the sense that do you look at, okay, whether the landslide has occurred or the impact of that, because you're moving from forecast to warning there, right? So when you're talking about validation of the system itself, so what is the kind of key points that you kind of focus around? Yeah,
Thank you, Nicole, for this question, which actually needs to a lot of time to properly be discussed. Actually, you do have first the different system components. No, you have validation of the landslide susceptibility model, validation of the probabilistic model, and this is the modeling itself. But whenever you combine this information and you aggregate and you use different algorithms, as you said, you do have a different information that you need to validate. And then basically what you do normally, we do have a handcasting capability. Whenever we have past information, we rerun the modeling entirely for those information, and we look at how was the system predictions. And this can be done for several different rain forecast products, but even for different possible combination of these products. There is, as you said, also the importance of comparing the warnings, because finally this is the warning. What we are doing now, we have a sort of a validation, we are using as a validation the warning raised as a consensus-based phase by the civil protection centers. So basically, we do have a sort of a observation, no? We are able to compare. We are working a lot on that, so this is one possible way, but this is how we do it. Yeah, thank you for this interesting question. Okay, SAR interferometry model, as far as I know, don't apply to all the kind of movements. Okay, in particular, the fast-moving movements are not detected by SAR interferometry because the limitation of the wavelength. And there is another important limitation, which relies on the acquisition geometry of the satellite product. They are not able to detect all landslide in all the conditions. They are moving up towards North Pole and towards South Pole, and they are looking right. This basically limits the detection on these movements, which have significant movements along this line of sight. So you do have this limitation. As said, you may try to integrate these two information to see if for some kind of landslides, in particular in the incipient phases, in the phases before the collapse, are able to detect this. But normally those are working better for specific landslide targets, including slow-moving landslides, which are not which are not really the focus of these systems. These systems tendentially want to predict rainfall-supported landslides, which are tendentially a bit faster. But there are technological advancements. They say that in the new, for instance, in the new Sentinel missions, they will even add, or in some constellation, they will even add satellite constellation which moves east-west instead of north-south. This may improve the spatial coverage of these systems, and even the use of different wavelengths will possibly give some information.
Sir, before we move on to the next lecture, may I please request our DDG NMH4, Dr. Shoibal Ghosh, to come forward and present Dr. Rossi with a token of appreciation. Thank you, sir. So as per our schedule, the next talk was by Sabrinathan Chellamathu. Is he present here? No. P. Devangan and team. Mitali Sinha, Dr. Ashwani Raju. Okay, so I guess we can move on to the next topic by Diganta Burman. Vulnerability Assessment of Living Root Bridges of Meghalaya, India. Do you need that, sir?
So in the meantime, I would request to please find out whether these three presenters, they can, after this presentation, they can do their presentation.
A very good morning to all the dignitaries. I myself, Diganta Burman, senior geologist, is giving a presentation on a very interesting topic, living root bridge. Living root bridge is a symbol of nature conservation as well as community work, because these bridges are mainly made from the roots of a particular plant, that is Ficus elastica. So my presentation will be, in this particular topic, will be introduction, location, objective, geotechnical assessment. I will be presenting about 9 living root bridges, which will be studied in my this study, and conclusion and some general recommendation for each bridge. So this living root bridge, in local language, it is, in Khasi, it is called as Jinkingsri, which are the example of indigenous bioengineering and cultural heritage for the state of Meghalaya. These bioengineering structures are not built in overnight, it is built in a decades. Actually, some of them are built over as old as 500 years also. These are showcasing harmonious blend of human ingenuity and nature. These bridges are formed by guiding and intervening the aerial roots of Ficus elastica. It's a locally available species only. And as per local community, around 70 living root bridges are present in East Khasi Hills and West Jaintia Hill districts in Meghalaya. These living bridges are why significant? Because of its eco-friendly nature. There is no concrete and other things has been used in this particular bridge formations, as well as adaptability to high rainfall area, because Meghalaya is the highest rainfall region in entire India, as well as Cherrapunji is the highest rainfall area, and Mosindram in the world also. So, and these are unique attraction for sustainable ecotourism, because it's a attractive spots for tourism also, and symbol of cultural heritage and environmental conservation also. These living root bridges are already included in UNESCO's tentative heritage list in the year 2022 also, because of its unique cultural and natural significance. These are the 9 living root bridges which I will be discussing during my presentation. There around 8 are present in East Khasi Hill districts, and 1 that is Swiss Inkyu root bridge that is present in Jaintia Hill district. So what are my objectives for my study? In this particular study, I mainly evaluated the slope stability in an area, in and around areas of each bridge. Also, it assess the human-induced as well as natural threats that are for these bridges. Also, analyze the resilience of these root bridge structures under varying geological and climatic condition also. It's also based on this assessment, I will recommend the remedial and conservation measures for each of these bridges. Also, during our remedial measures, we also look into consideration that natural measures are mostly being employed. And also it provide a scientific basis for inclusion of these living root bridges in long-term heritage management and UNESCO conservation framework also. So in geotechnical assessment, first living root bridge which I will be presenting is a Wasohut living bridge. It is near Peninsula, it's near Suthim village. This bridge has a length of around 4.5 meter and height from the riverbed around 1.5 meter. It is founded on pink granite gneiss only, and most of the structural discontinuities, there are two joints are present. They are forming wedges, and these wedges are also prone to failure also. So this living root bridge probable cause of instability in future are mainly unfavorable discontinuities on the right bank and deforestation near the bridge. Because of people now, because of population, people are building houses and other things, so they are cleaning the forest, because that's why some of the slopes are vulnerable also because of that one. So what are our conclusions are? We are suggested to construct stone pitch guide walls on both the banks in a slightly slanted angle so that water will be diverted away from the roots, that is from abutment areas, and channel maintenance, because most of the living bridges, some boulders are also there, present upstream and downstream. So when high floods are coming now, so that will creating sudden floods also. That will affect the bridge because water will coming directly to that bridge. So for that we are asking for manual cleaning of the river banks also. And bioengineering, mainly deep-rooted local species plants can be planted on the overburdened portions of the slopes to improve the slope stability. Next bridge is a Umlingo Living Root Bridge, that is around length of 10 meter and height from the riverbed is 2 meter. This is also founded on granite gneiss, and 3 joints are present on this particular bridge, and out of these 3 joints, right bank joints are vulnerable. We have plotted for kinematic analysis. So unfavorable discontinuities on the right bank will be a cause for failure also in the future. Steep unprotected slopes on the right bank also can pose threat to the bridge. And we have suggested for guide walls, construction of stone, locally available stone pitches guide walls on the toe of the right bank in order to prevent future failure. Also rock bolt in the direction of north 200 degree, 3 meter length, to arrest if some blocks will be coming out to and fall on the bridge to damage it in future. Third bridge is Uak, which is living bridge. This is having length of 10 to 12 meter. Height from the riverbed is around 10 meter. This particular bridge also, right bank is vulnerable due to wedge daylighting towards the river. And moreover, some large dimension boulders are also present on the upstream of this particular living root bridge. So water, when high flood comes, this water will hit this living root bridge, so it's making it vulnerable. So we have suggested for construction of stone pitch guide wall on the toe of both the left bank and upstream and downstream in order to prevent future toe cutting, as well as channel maintenance through manually to remove the rock boulders so that water can free flow and without causing any damage to that living root base. And chain link shortcut can be also done on the left bank. Fourth bridge is Tirpa Mola living bridge. This is one of the beautiful living bridge, but though tourists generally won't visiting this bridge because of its difficult tracks. In this bridge also, foundation is on mainly on the granite gneiss also, and quartzite. And in this particular bridge, also there is a right bank is vulnerable due to wedge daylighting towards the river, and unfavorable discontinuities and water clogging in upstream due to large boulders on the riverbed are 2 main causes for which may create problem in future. So guide walls we have suggested, as well as manual cleaning of the channel also been suggested, and chain link short kick on the leg bank to prevent and entrap the falling stone in future is suggested. The fifth bridge is Lingtang living root bridge. This is living root bridge. In this particular living root bridge, one bank to NC2 rocks are there, but other bank there is a boulders on which this bridge has been founded. So in this bridge, the right bank is vulnerable due to presence of perennial nala, old slide, and a constant deforestation. But left bank, that boulder is also vulnerable because of erosion, toe cutting. This boulder is also gone vulnerable. So we have suggested for guide walls on the left bank that to protect that boulders, as well as slope modification on right bank to prevent already present existing slide also. Channel maintenance also been suggested through manually, and bioengineering methods are been suggested on the right bank where constant deforestation is there. And sixth bridge, Mingyang living bridge. This living bridge already been devastated because of a flood that has been caused in the year 2021. And moreover, some road cutting activities also going on upstream. Those road cutting marks are already been dumped through slope, so that when that 2021 some devastating torrential rain has come, that bring all those boulders to that bridge, and it got stuck under the bridge, and water channel also migrated towards the right side. So that water migrated and that living bridge got damaged also. In this particular living root bridge, we have suggested for manual removal of the transported boulder below the bridge and dump on the left bank, construction of gabion and retaining wall on the right bank to prevent tow erosion and during high flow event, and build 2 check dams upstream to arrest further that debris cannot flow down to that river bridge. And long-term measure, as we have suggested for periodical dredging of the nala bed and removal of the boulder upstream of the check dams, and establish a 100-meter buffer zone around this particular bridge to no construction and deforestation should be done in future to prevent this heritage. And last is Sui Singku living root bridge. This is in Jaintia Hill district. In this particular living bridge, there is a peculiar problem that village drinking water supply pipes are being passes through this particular bridge, which are heavy in size. So it is creating a problem to this bridge constantly. So we have suggested for removal of those water supply pipes from the bridge, so that weight on the bridge will be reduced subsequently, and life of the bridge will extend further. And this is Novobet living root bridge, which people usually visit because it's a tourist attraction. This particular bridge, mainly people who visit, they visit this one only. So in this particular living root bridge, already conservation measures are being done, but still we have suggested right abutment conservation through retaining wall already present, but it must be present in it must be done in a slant angle in order to deflect the water away from the bridge. Left abutment also we have suggested for retaining wall. River channel also boulders are present which need to be cleared manually, and limit the number of personnel and visitors on the bridge to increase its lifetime. So on conclusion, most of the living root bridges are represent a unique integration of bioengineering and natural architecture, many exceeding around hundreds of years age, and most of the bridges are found on quartzite, granite gneiss, and sandstone. And anthropogenic activities, those are affecting these bridges, are road cutting, unplanned dumping, and vegetation clearance. And hydrological impact from the flash flood and upstream boulder deposited in a recurring hazard that alter the nala courses, which will be affecting many of the bridges. Despite localized instabilities, these bridges are still persisting. They remain good after those harsh conditions also. So it is also remembers us that these are ecologically very good. And general recommendation, all the bridges we have asked for tow protection work and guide walls, channel maintenance through manual cleaning, slope maintenance, management and bioengineering methods can be used. Debris dumping should be done in a designated sites only, not through the slope, so that it will affect the bridges. Hydrological controls, check dams must be, can be done on upstream to protect the debris to flow down to downstream. And heritage, as a heritage protection measure, we can declare buffer zone of 100-meter radius around each bridge to restrict construction, deforestation, and heavy tourist flow, and limit the number of visitors at a time to the bridge. And monitoring, we can do pre-monsoon and post-monsoon checkup to each of the bridges and involve local people for maintenance of these bridges to use their traditional knowledge. Thank you all.
People have questions now? Yes, please.
Very interesting work. I've never heard of this, to be honest.
Thank you, sir.
But what I was worried about is that this is a pretty nice example of natural structures, right?
Yes.
But I noticed that some of the interventions which you have been suggesting, like retaining walls,
Yes.
etc., aren't they, or wouldn't they kind of cause more problems than retaining the natural beauty and the natural
Yes, sir.
integration, as you mentioned?
Sir, actually, we have suggested as far as possible natural methods should be used. On that one, mainly they are doing the retaining structure through gabions. From that locally available boulders, lots of boulders are in and around each side. So we are using those only. And that rock bolt and other things are optional only because they also want that natural process should be used in this particular conservation process. Because they want to use a criteria, probably some criteria is there, UNESCO World Heritage inclusion, so natural, local traditional knowledge will be used for conservation of those. So those are that rock bowls and shortcuts are optional one, but Gabion walls, that can be done from locally available without much of interaction from anthropogenic cause.
That makes sense. Thank you.
Sir.
Hey, Mr. Roman, very interesting topic as well as presentation. You had written somewhere that some efforts, aspirations are there to nominate these
Yes, sir.
structures to UNESCO heritage.
Yes, sir.
Many efforts have been done in that conservation guidelines will be required to submit
Yes, sir.
nomination to GS. Any progress in that field?
Sir, actually, they have submitted for that tentative first one. After that, they will be doing detailing from east side. That's not been done yet, but that will be done, sir. Because for that, they require detail. This was a preliminary first-time assessment only, most of the bridges. Around 9 bridges. It has been done through a multidisciplinary teams. From where the geologists, botanists, geologists, all the peoples are visited, and after that they have submitted for tentative list inclusion, and it has been included. Later on they will do the detailed one for each site again, and it will be done in around 70 sites they have selected, probably 10 or 15 sites they will do detail, and they will submit and as a whole for that one only. Thank you, sir.
So we are moving on to our next session. Rajiv Ranjan, is he present or any team member? Sriram? Okay, so I guess Dr. Nikhil Vasu from BGS will be presenting the next topic, Advancing Landslide Forecasting in India. Please welcome him. Thank you.
So, hello everyone. First of all, thank you very much to GSI for organizing this event, and and for accepting my abstract to present at this forum. So, today's presentation is based on one of the ongoing projects that we have in India, in southern India, that we are working in collaboration with University of Kerala and also GSI. So So this particular project, just to give a quick context, is based on ongoing BGS IGRD program. So this program is basically looking at the global challenges and trying to kind of tackle some of the challenges using for various type of challenges around the risk to urban environment, the security, the water resources security, and also the mitigation of geohazards in many parts of the world. So this particular project that I have within this program was mainly focused around the tropical residual soils. And the main reason for us to select that region is because if you look at this figure, this is the data from Frood and Petley in 2018, which shows the the landslide distributions globally and its impact as well. So it's basically a fatality-based database, and if you look at that red band here, which is basically where we define as a tropical region. So we can see there's a whole lot of landslides around here, and I think this was also referenced in Dr. Seibel's presentation as well, that the fatalities and the impacts from these landslides are much greater in that location, and that might be because of the changing climate as well as the rapid development activities that's happening in that area. So and also another piece of information here is that there are landslide inventories, but especially when you look at some of the temporal information that's required within this landslide inventory, that's usually, incomplete or is scarce or is poorly maintained. And to kind of clarify, I mean, that's just not the problem in this countries. It's also a problem in many other parts of the world, including the UK. But the impact that you would see from many of these landslides are much greater in this part of the world than many other. So we, as part of this project, so we started to look into some of the landslide threshold works, which was mainly using more statistical based methods. So we did a review because we wanted to understand whether many of the statistical models have been developed using a fairly good amount of data. So as part of, in the first year, so we conducted a quick kind of a review through a number of publications, mainly around the countries within what we defined as a tropical region. And what we found was that many of those models that was developed in this part of the world, I think there were a lot of limited. So there was a lot of limited amount of data that went behind calibrating and also for validation. So technically, it's the reliability will be relatively low. So this piece of the work, so I will not go into detail because this was something I presented in EGCon 2022 November, also organized by GSI. But one of the takeaways from this was that you cannot always just rely on just keep collecting the data because that takes a long time. So instead, you also need to have some kind of a parallel approach where you can try to understand some of the ground conditions and how you can bring those understanding into some kind of a model, which can also inform how the rainfall interacts with the ground and whether there's a possibility for landslides to occur. So this was a gap where we were trying to inform through this project, and in order to do that, so we selected the site in India, and that again comes from the legacy of working in the country through the Landslide project. So the methodology, as you can see on the right-hand side, so this was kind of formulated around 3 stages. So the first stage was actually trying to, so we're trying to use this approach over a large area. So we want to try and pick out, a bit more distinctions within the area as much as possible in terms of, whether there's a lot of differences in terms of geomorphological conditions or even as simple as the rainfall patterns, whether there's some differences there. Because all these differences are also going to inform the way the landslide processes might be a bit different in in many of these places. And therefore, it will also influence the way you define your conceptual models or some of the assumptions behind these models. So once you've kind of divided some of these areas, then in the next stage, you kind of go into try and developing some of these, try and tune or develop some hydrological model. And the outputs from the hydrological model, for example, it could be soil saturation or pore water pressure or even water table changes that can be incorporated into some of the slope stability modeling, or basically some geotechnical assessment, and that then could be fed into into some kind of assessments which could inform the triggering of landslides. And on the left hand side, so you can see there's 4 different key skill set that we had within our project. So that's like hydrologists, hydrogeologists, geologists, and geologists. So landslides being such a complex topic, so there is a lot of interaction of different processes, and that also needs to be reflected in the team that you have. So for our project, so we had these different group of people who brought some expertise from their groundwater modeling or hydrology or hydrogeologist. So that kind of tried and inform a bit more detail into some of the models that we were trying and developing in this project. So the study area that we selected was in southern India because, again, because this project is informed in terms of the tropical regions, and because we have the past working collaborations here in the country, so we thought Kerala would be a good site to start working. And Idukki, again, in yesterday's presentation as well, so there was reference made to the Kerala 2018 event, so Idukki had seen a lot of landslide events in the past, including one in the 2020. There was a big debris flow event in Rajamala, Pettimudi site. So yeah, so this was this also resulted in massive impacts. There's fatalities associated with this debris flows as well. So we have selected this entire district. So we are trying to develop some models for the entire district, and the rainfall. So the bottom right-hand model shows the rainfall distribution, the long-term, the annual rainfall distribution, and you can see again there is some less amount of rainfall on the eastern side, and there's larger amount of rainfall. So there's some kind of rainfall shadow on the eastern border of the district. So just in terms of the methodology, as you might remember from my previous slides, the first step was the domain assessment. So all of this work was also, so we are co-supervising a PhD student. So the PhD student helped us to carry out a lot of these work. So that in the domain assessment, so we tried to use some simple criterion to try and divide the entire district into a few different domains. So these are the steps in which we tried. So in the first stage, it was broadly divided into like these 3 domains, looking at the regions, so lower plateau, midlands, and what was like domain 3, the highlands. And further details were added, or further delineations were then done for each of those domains, based on some of the other factors, like whether there are some rainfall shadows, some transition zone, and so on and so forth. So these has been carried out using more simpler kind of schemes, but obviously you can bring in more details, like if you have more detailed information around the structures, the geology, obviously you can try and bring that and create a bit more delineations within here to inform your process. So once that was done, So we moved on to the next stage of doing the hydrological assessment. So this was done using an in-house BGS model. So it was called the Zoodrim model. So this is a hydrological model which is traditionally being used in the BGS to model flooding and droughts. So we tried to tweak the conceptual model to fit some of the landslide processes here. And this model would give us some information around the runoff, the recharge into the aquifer, and then for the saturated zone, some of the lateral flow of the groundwater as well. So this model is able to kind of able to model these things. But this is a bit different in terms of how in the traditional geotechnical literature as well, there's already a lot of hydrological models, but this works in a bit different, but it brings in the perspectives of the hydrologist side of things. So once the hydrology models were done, so the output, so mainly the soil saturation, would be then fed into the slope stability. So the type of landslides that we have assumed for this work is mainly around the shallow landslides. So you can have shallow slides, you can also have debris flows, but the debris flow mechanism that we have assumed here mainly involves a shallow slide which then is mobilized into a debris flow. So there are different ways in which a debris flow can be initiated. So we have just assumed one of the triggering mechanism associated with that debris flows. So this is an infinite slope-based assessment that's been carried out, but then we used a Monte Carlo simulation to try to capture some of the uncertainty around the geotechnical parameters of cohesion and friction angle. So this is a table that just shows some of the input data that's gone into this model. So I won't touch on all of these things, but one of the important one was the rainfall. So this was obtained from ERA 5. So that's a European, I think it's a European medium EMCWRF. So I don't remember the entire, but that is looking at the short-term kind of a medium-term forecast models. So this particular ERA 5 data is output from there. But we also had to modify this rainfall because we already had some rain gauge data in Idukki, but the long-term average from that data kind of bit differed from the model data, so we had to kind of make a bit of adjustments to the ERA 5 data. So that was done. And the resolutions of these models are, I think, is about 25 to between 25, 30 meters. So it's 25, 30 kilometers. So this is quite a very coarse rainfall grid data that goes into the model. And another bit of information that was also not easy for us to get for the soil's depth data. The soil depth was also something that we had to, there were already some empirical relationship that exists for Idukki. However, it did not kind of fit with some of the observations we had from the field observation. So we had some informations around some of the landslide events that happened in 2018, and there was some soil depth information that was captured during that. So we developed a relationship between the slope angle and those slope depth, soil depth information to then try and apply it over the district. So some of the other informations around the geotechnical data, again, we obtained it from the literature because there was nothing that was already existing specifically for Idukki. But because we are using a Monte Carlo type approach, so we had the opportunity to kind of try and give a lower bound and upper bound and try to explore that parameter space. So now I'll show you some of the preliminary result because this is an still ongoing research. So these are some of the results from the model. So for hydrological models, so we had to start with the calibration of the model, and traditionally for in the hydrology side of the discipline, they always calibrate using the discharge information. So they need gauge station data to try and calibrate some of the model parameters that goes in. So that includes parameters like your runoff information, the base flow, and you need your total flow information. But for Idukki, so we do not have that kind of information generally from, maybe that is existing from the CGW B or other kind of departments. So instead, we came across this open source information. It's a global model called the GeoGloves Hydro Viewer. So they have some observations around the gauge station. So that's an open source kind of information that anybody could actually get. And we use that information to then try and calibrate our models. So once, I think there are about 9 gauge stations, yeah. So there are 9 gauge stations across Idukki that we got from this global data, and that was used to calibrate the model. So this is how some of the results looks like. So the model produces the output for the entire district. However, we took the results here that's shown, or some of the examples of the results are taken from these clusters that is associated with the 2018 distribution of the landslides. So we took those points to look at how the soil saturation informations are different. So if you can see the graphs on the right-hand side, so the top one actually shows how wet the landscape is, on the duration for how wet the landscape remains to be saturated. So these star points, the red stars, you can see are actually the dates, the durations corresponding to the 2018 events. And for majority of them, you can see how these are above the median values. So these kind of gives some kind of a sense check that, yes, that was an extreme rainfall event, and because of the amount of rainfall which fell on that landscape, so it kept the landscape wetter for a longer period of time. So these kind of outputs, it gives you some, the scientists or the users to kind of give us some kind of idea as to how the landscape is working in relation to the rainfall that's impacting the ground. So once you have this soil saturation, so this can be then incorporated into the geotechnical assessment. So on your x-axis, you have a soil saturation data. On the y-axis, you have the probability of failure. And the probability of failure is, you get that probability because you're running the factor of safety several times using the Monte Carlo type of simulations. So in here, you can see there's a good relationship between the steepness of the slope angle and the soil saturation. So as the slope starts to get more steeper, you just require lower amount of the soil saturation for the failure to happen. And some of these triangles, the red triangles, corresponds to the past failures of 2020 and 2018. Majority of this is related to that one event, 2018. But because each of them have happened in different slope angles, that's why you can see that spread here. And many of them, they are on, towards the higher saturation end. That, again, it gives you some kind of a sense check as to whether, these events were, again, triggered by very high amount of soil saturation that exists within the landscape. But all the gray dots here, so these are the background events from your time series. And you can see there's possibly a lot of, false positives as well. So therefore, there's a question of how do you validate a lot of this? And it's a ongoing research. So again, it's always, I would be happy if you have any feedbacks again on how we could kind of try and take this work forward. But again, because we have very limited landslide informations around when it has occurred, again, that for the moment constrains us in terms of how you validate this kind of models. But at least what it does is it gives you a sense check, as to whether there is what the potential might be when you combine the rainfall with that slope types, whether there is high possibility for a landslide to occur or not. But as in Dr. Rossi's presentation, again, it's still kind of a theoretical kind of a work. So it might be very different once you start applying it on the ground, and that's what we want. We want to see how well this would work once you start applying this to more practical applications. So just to come back to the key takeaway. So through this project, what we wanted to do was to kind of provide a framework or a workflow to try and bring different ground informations to inform the landslide triggering at a much more regional scale. And it was a very kind of a nice project in the sense that we had different scientists from different disciplines trying to kind of bridge some of the gaps in our understanding in terms of the hydrology or geology or the engine geology side of things. And another key point is that this is not a standalone solution. It needs to be used along with other type of approaches. Again, this was a point that Dr. Rossi has picked up in his presentation as well. So this only gives the experts some kind of a sense check as to how the landscape is, whether it's wet and whether it's kind of now becoming drier as the rainfall is moving away. So it kind of gives a sense check. So it might be very useful for this kind of applications. And now we are trying to do some kind of ongoing work around understanding the parametric kind of sensitivity around some of the input parameters we've used in the hydrological model, and also trying to see whether mapping this into a slope unit would give us a bit more consistency of results. So it's ongoing research, and March will be the end of this project. So we hope to get a bit more information, a bit more results by that time. So thank you very much. And I also would like to acknowledge all the support from colleagues at Geological Survey of India, because we have taken, we had undertaken 2 field works, first at the start of the project in 2022 and last year, and we had all the field support from GSI colleagues. So thank you very much for that. Thank you. I can hear you. That's.
Let's go with this.
Yeah.
I have a question related to the uncertainty of the parameters, because as you mentioned before, there is a lot of problems with them. So based on the results you showed before with this probability separation,
Yeah.
so in order to create this kind of plot, did you use the central value after your modeling? I mean, you assume a sort of Monte Carlo modeling.
Okay. You use a sort of Monte Carlo modeling, exploiting all the variability and maybe a Gaussian approach with a limit, upper and down limit. And at the end, you only show the central value, or there is in this plot some uncertainty also that I didn't get. Thank you.
Yeah. No, that's a good question. Yeah. So obviously, we had fit a log normal for the cohesion and the friction angle, as usually seen for the geotechnical, in the literature. So yeah, so we did. So for plotting this, it was actually like a median that we've selected. So there is actually a variability in there that I couldn't show, because otherwise the plot looks very scary. So so just to keep it clean. So yeah. Thank you.
Okay,
Yes.
it's an excellent presentation. Yes, I have 2-3 queries. One is that, as you know, in Indian landslide conditions, there are some terrains where perhaps the soil moisture is actually might be one of the nanometer rotations, 80 nanometers, and other sort of open sensors. Will that output help you to develop or make out some sort of threshold in these EWP registers? Because EWP is in our strategy area also.
Right, yeah. No, thank you very much, Dr. Saibal. It's yes and no. It depends on, I'm not trying to go around this question, but the reality is depends on how your soil moisture, how your distribution of your soil moisture, the sensors. Now, for example, in the UK, so we have a slope in the north part of the UK. It's called Hall-1 Hill, and that one slope has been instrumented using the electric resistivity tomography systems that looks at 3D way in which the slope gets saturated. You have point sensors, you have fiber optics, so that is looking at both soil moisture as well as how the ground deforms according to that. But for that itself, trying to develop a threshold was a bit difficult because trying to get that kind of a relationship between the rainfall as well as that 3D changes in that slope because of heterogeneity became a bit of a challenge. But again, that might be because you're just looking at one slope and you're looking at a lot of the heterogeneities in there. But there are papers. I think there are some Swiss researchers and even, I think, Amrita University as well, I think, for the Muna. So I think researchers have tried to build that relationship between the rainfall, pore water pressures, or rainfall and the soil moisture. So it might be better than having nothing. So you could definitely have a look at that data of the soil moistures and look at if you can actually have any kind of a real relationship between the rainfall as well as the soil moisture data that your instruments are showing. So we can definitely have a look at it to see whether it can be developed or not. Because again, I think we have to be very careful as to how we place many of these instruments. We need to be a bit smart about that as well, because I think we need to have an understanding of how different some of these catchments might be, what the variabilities might be. So I think that kind of a study also needs to be undertaken before we decide where some of these instruments might go. And I think that will also influence whether you can get that kind of a good relationship between the rainfall and the soil moisture. So yeah, so it's a gray zone. It's not just a yes and no kind of answer. So yeah.
Yes, Mr. Nikhil, very good presentation.
Thank you.
But your model is yet to be completed. It is under development. So
Absolutely.
we cannot talk about the validation of your model and the estimation of the uncertainty. One thing, you have plenty of data, all the layers of data which affect landslide is there, and it is very suitable case for application of machine learning to make your machine learn with your data and give some predictions. So in that front, some work is there. Definitely some work should be there, must be there by different progress. Whether you have taken such type of work.
In BJ's, my other colleagues have done, and they are actually doing, one of the projects is actually in Italy. They are trying to develop a threshold based on some of this machine learning technique, but not for this work, because our primary objective was to try and understand some of those signatures around the ground information and, trying to get a good understanding of how the soil moisture changes within the ground. So it was, trying to bring that baseline information first before we jump to that, more advanced kind of model. So that was the whole objective.
Okay.
Yeah. Thank you.
That is the end of the presentation. So
So we had circulated a message in the WhatsApp group for oral presenters. Have any other presenters joined here? No, sir, I guess this is the last presentation then.
in that case, we can conclude this technical session 3 in VR in beta is development of regional early warning systems in India. And initially we started with 2 places. One is in Darjeeling and another one in Tamil Nadu. And we then started calibrating our models and issuing some bulletins. So now this early warning systems we have put up in more states, and our work has spread, and it will need basically because for issuing the bulletins and which will be actually to remove the uncertainty, and in case of a widespread probability of occurrence of landslide in an area, and then maybe involving the civil authorities. So it will take some more time. It is work in progress, and lot more calibration would be required because the chances of the improvement of the model should be that so much that when we actually really we are informing the civil authorities, then civil authorities have to act and the evacuation process etc. has to start. So to reach that stage will take some time, and it is work in progress, and we need to continuously calibrate and validate our models till we reach that. Thank you.
Yeah. We geoscientists mainly know how mineral discoveries, but this is another phase of geoscientists which directly connects with the society. So it's very important phase of geoscientists. A lot of work has been done in the prediction of disasters like floods, cyclones, lightning. They can be very accurately predicted nowadays, but a lot of work is there to be done in the prediction of landslides. I think we have to develop with all these efforts and models to come up with such a result which ultimately predicts landslides as well in the same accuracy. There may be limitations here and though, but this is the field where a lot of work is needed, is to be done, and I'm quite hopeful the scientists working in this field will come one day with such type of solutions. So my best wishes to everybody, though only 3 presentations were there, but all presentations has the impact on the society, and they were wonderful presentations. So by this I think we can conclude this session. Thank you very much.
Thank you, Honorable Chair and Co-Chair, for your insightful remarks. So as we conclude this intellectually invigorating session, we extend our sincere thanks to our keynote speaker and other speakers for the remarkable contributions, and thank you to our Chair and Co-Chair for guiding the proceedings with such grace and clarity. Thank you, sir. So may I now ask our DDG SU Maharashtra, Dr. Vibhash Sen, to please give our token of appreciation to our Chair and Co-Chair. Thank you, sir. So thank you, everyone, for your patience. We'll now resume again at the next session. Lunch will be served at 1:30 in the main hall. Thank you.
कॉपी कर दो
एक मिनट सर, एक मिनट। क्या कर दो?
सर का कॉपी कर दो ठीक है।
हाँ जी।
इसमें बता देना सर का कौन सा है।
Sir, is this one or session? Geophysical insights, imaging the Earth.
I think so.
Okay.
What's your name? Just ask me.
I'll just check, sir.
Yeah, that's better. I haven't seen a program, but is there a program anyway?
Yes.
Yes, it is here. Oh, is it?
So you're presenting. Oh, okay, sir. Okay,
That's-
sir. High
that's this
resolution.
all?
Yes, yes, yes.
Okay.
Thank you.
कॉपी कर दो। कैसे नहीं लगेगा?
Yeah.
बैक करो पहले।
Sir, six, na? हाँ, sir.
Okay.
Yes.
Yeah.
Thank you, sir.
Thank you. What time would have this?
हाँ, 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 sir. Yes. ये वाला? हाँ सर है, एक्चुअली मुझे थोड़ा मंगवाना पड़ेगा। मैं
मंगा लीजिए, मैं कर लेता हूँ। मैं डाल देता हूँ।
हाँ।
कौन सा बिल कुछ है?
हाँ सर।
उनको मंगाइए, दे दो, ठीक लगता है। Two.
सो 6 से एक मिनट यहाँ पे नहीं, वो ये अलग से नहीं खुलेगा क्या?
सर ये मैं कर देती हूँ।
हाँ, यहाँ जाके इसको कॉपी कर देता
ये वाला ना?
हूँ। इसको 2 कर दीजिए।
ये वाला है ना सर? सर आपका नाम है?
ये वाला
हाँ हाँ, प्रदीप मौर्य।
नो यस दिस इज नेम, नेम बीजन, सोरेन बीजन। वहाँ अपडेट तो यहाँ अपडेट नहीं है।
हाँ हाँ हाँ।
His name
We
is
changed the presenter with very short notice. Sorry.
It's okay. Beyond, right?
या सो इसको 2 कर दे। 2 हैं?
I'll just write his name.
Correct.
How do you pronounce your name?
Difficult. Søren Bjørn. Søren Bjørn is fine.
Okay, okay. And the doctor, any connotations? I don't know.
I'm a master in geophysics. So.
और मैं दूसरा ले आता हूँ। ये तो ले आया एक प्रकाश चौबे हो गया, ये हो गया। नहीं, नेक्स्ट सेशन का है 2:30 के बाद।
हाँ सर, ये नेक्स्ट
ये निकाल लूँ मैं?
हाँ सर, ये 2 ही हैं, अभी और तो भी होना चाहिए।
अभी आएंगे लोग, हम तो 2 लाके कॉपी कर दी।
सर का
पाल तो है, संजीत को नीचे रह गया।
अच्छा।
मैं संजीत में आ रहा था, मेरे साथ रह गया नीचे कहीं।
और ये इनको भी नहीं जानती हूँ।
ना मैं नहीं जानता, आरबी सिंह नहीं जानता। ये कहाँ के हैं?
अखिलेश कुमार वर्मा।
अखिलेश तो आया कि तो जेसाई का लग रहा है ना?
हाँ हो सकता है।
अखिलेश तो जेसाई का है?
अच्छा, ना सर, केपी सिंह।
पता नहीं।
ठीक है, तो ये दोनों का ही
हाँ
है।
अभी नेक्स्ट सेशन में
ये वाला है।
इसमें ये तो नहीं है, ये एब्सेंट है। मेरा पेन कहाँ रख दिया? ये तो नहीं है, ये एब्सेंट है। क्योंकि आपने ऑनलाइन के लिए मना किया ना।
हाँ,
ये तो
एलाइक ओवरलैप,
नहीं, ये तो इससे पहले कैथरीन दिखे कहीं। हाँ
कैथरीन ट्रफिक।
हाँ, ये है। ये कैथरीन जो है आई हुई है।
हाँ।
मैं उसका प्रेजेंट लेके आ रहा हूँ
ओके, शशांक नारायण वर्मा
ना। ये आए तो हैं।
और रिया तिवारी।
रिया तेवतिया दिख तो रहे थे।
ठीक है सर, मैं और एक फोल्डर क्रिएट करके रख देती हूँ
हाँ।
यहाँ पे। वो रहेगा हम लोग का 5 o'clock।
जल्दी भी हो सकता है ना, क्योंकि खाली है नहीं।
सर बीच में वो पोस्टर सेशन रहेगा फिर।
अच्छा, ओके, इसलिए बहुत करते हैं।
ग्रेगरी स्ट्रीट।
ओके, रिजल्ट लेके आता हूँ।
ठीक।
आपका नाम क्या है?
मैत्री चक्रवर्ती।
Yes. उसको अभी बोलो थोड़ा ऑब्जेक्शन कम लगाए, ठीक है। और एक चीज़ है बेसिकली
So this is, where is the paper? पेपर मैडम के पास है हाँ कॉपी तो कर दूंगा वो पेपर है ना जो नंबर लिखना है हाँ कौन सा कितने बजे
सर 3:40
एक्चुअली मैडम नहीं है लंच पे गई है
कोई बात नहीं There is one here.
here it is there जरा बुलाओ यार मैडम को देखो तो मैं कॉपी तो कर दूंगा उसको नंबरिंग करके देना पड़ेगा ना
It's not the 2 point, you have to go back.
Which one?
Yeah, it's not the 2.30.
Which one?
Because it's not this, it's not in this one. You have to go back. Yes, no.
No,
I
which
mean,
one? Which one? Your this one?
Yes.
Copy.
Okay.
And
Go here. Here. Yes, today.
day 2.
And 5 p.m. session.
This one, 5 p.m. session?
Yes, that one.
And your number is
How can I say that?
1, 2, 3 like that.
It's over there or not?
हाँ 1, 2, 3 ये पेपर होता तुम्हारे पास नहीं है She's having
Okay. So mine is this one.
before then how many people?
Okay. And 3.
Three.
And the third one.
3 so
Session 5.
3 Catherine Prophet and what is the subject or something?
Yes, new horizon for geological survey.
New Horizon.
For geological survey.
New Horizon
For geological
for geological survey. Okay. I will send to let's take. Yes. ये 2:30 start होगा. So yours 2:30? 5. 5.
बजे से है
2:30. लाइव कॉपी करें आपका नंबर कितना है व्हाट इज नंबर संजीत पाल 1 मे बी 1 2:30
सर अब लंच किया
भूख नहीं है वो सब खाना देख के डर लगता है इतना खाना रोज खा रहे 2 दिन से ट्रैवल में अभी आके आ रहा हूँ ना 2:30 पे अभी टाइम है ना सर आधा घंटा 1 ना कीनोट हाँ कीनोट 1 कीनोट कौन सा खाली ये ऊपर वाला कॉपी करना दोनों?
दोनों कर लीजिए, पता नहीं वो एक वीडियो है।
अच्छा, उसके एसोसिएट होगा ना, फिर यही कॉपी कर देता ना।
हाँ, और उसमें एस्केप ऑल कर दीजिए।
हाँ, एस्केप ऑल कर दूँगा इसको। क्या हुआ, कॉपी नहीं किया? काम नहीं कर रहा है? GSI यही था ना? कॉपी तो किया मैंने, कॉपी देन डेट 2:30 PM, यहाँ पे पेस्ट। अब हुआ। देख लूँ चल रहा है कि नहीं चल रहा है। इसको पहले तो रीनेम कर देता हूँ ना, की नोट ना, की नोट एस्केप ऑल, ठीक है। चल रहा है, ठीक है। वीडियो कौन सा था? वीडियो
बहुत बाद है। चलिए सर,
हाँ,
जल्दी जल्दी 25 मिनट है, जल्दी जल्दी इसी में ही आएगा किसी एक में।
खत्म हो गया ना।
नहीं ना, ये वाला ये इसका।
ये वाला
हाँ,
कहाँ पे, कौन सा वाला?
हाँ, ये वाला यहाँ पे। हाँ
ठीक है।
हाँ, ठीक। चलो। ये यहाँ पे दिख रहा है ना लाल वाला, लो वेलोसिटी, ये साइड का डेटा, ये वाला डेटा सेंटर का लिया, वो वाला वो लगाए, बहुत सारा डेटा लिया एक एक ग्रुप में, तो ये वाला इस साइड का डेटा, और ये जो वीडियो दिखा रहे हैं हम यहाँ का डेटा है।
एनीवे एक ही बात है।
ये यहाँ पे देखो थोड़ा सा हायर आया, वहाँ पे और थोड़ा सा कम हो जाएगा, और ये और थोड़ा सा ऊपर जाएगा। ये साइड में है इस तरीके का।
नेचुरल इफेक्ट आ गया उसका।
वो चीज़ एकदम वो हमारा स्टडी के बाद ये किया, लेकिन और भी कुछ जगह में हम बोला यहाँ पे है लो वेलोसिटी दिख रहा है, बोला नहीं हमको तो ड्रिल करके बोला नहीं ये तो खिलाफ है।
सही है, चल रहा है।
आप करेंगे ना वीडियो कॉल? हाँ एक फोल्डर में सेम में ही डालना, एक वीडियो है एक जी सही
जी सही में।
हाँ
कौन सा है?
तो पीपीटी है
ये वाली?
हाँ और एक वीडियो है हेलिस
दोनों?
नहीं नहीं वीडियो है नहीं हाँ ये तो पीपीटी होगी ठीक है इसका भी इसका सेम फोल्डर में करना कोई एक बना के ना केपी सिंह के नाम से या ऐसे
ये डाइवराइजेशन है ना?
हाँ मतलब 3:40 के करीब है उनका फोल्डर बना लीजिए केपी सिंह करके उनकी क्योंकि वीडियो और वो दोनों केपी सिंह CGWB
क्या?
केपी सिंह CGWB
CGWB
इसके अंदर कॉपी कर दीजिए और एक दोबारा करना पड़ेगा
ठीक है
दोबारा पेन ड्राइव में जाइए
जी
बाहर जाइए थोड़ा USB में इसमें ये सही वाले में देखना वीडियो कहाँ पे है इसमें
वीडियो ये ना हेली सर्वे इन प्रोग्रेस
देखना
यही है।
हाँ खोलना एक बार हाँ हाँ ठीक है ये भी उसी फोल्डर में डालिए और ऊपर पीपीटी चला के देख लीजिए
इसमें डाल दूँ?
हाँ जी उसी केपी से पीपीटी ऊपर चला के देखिए
चलाने वाले क्या है कि यहाँ पे गए मैं सिर्फ कॉपी कर सकता हूँ।
हाँ
सिर्फ कॉपी कर सकता हूँ चलाने वाला कहीं बाहर
कोई
है।
इशू नहीं
ठीक है
वैसे F1 का आपका देने से हो जाएगा ना
नहीं मेरे को कुछ पता
चलो
नहीं।
कोई नहीं ठीक है आपने पेन ड्राइव
ठीक है
आपने डेस्कटॉप पे डाला ना फोल्डर
नहीं अंदर उसमें कर दिया
जैसा docs का है।
डाइप पे बना वाला।
अच्छा बना हुआ है
हाँ उस पर कर दिया।
इसमें लगाए लगाए
डाल दिया ना आपका रहेगा कि मेरे पास लाइट चेंज प्लस बराबर रहेगा CGW पोर्टल का नाम है ना CGW CGWB कर दो लास्ट में
ठीक है
बस ठीक है इसमें कीनोट सारे पाउसा
फटाफट नीचे आ जाना। एक ना पैक कर दिया, एक ना कार्ड स्कूप करवाया है। कुछ नहीं, खाली कैमरा ट्राइपॉड है और एक पावर केबल इसलिए बॉडी वाली भी अपनी थी, अपने बैग में डालते हैं। क्या हो गया?
इधर कॉपी करना है। मेरा नाम पे क्या ऊपर यही है ना? अच्छा ठीक है सर। इधर लिस्ट तो होना चाहिए ना कि नहीं सर, हमें बस में कोई लिस्ट नहीं है। सेकंड सेशन है सर आपका? हाँ 410 में कुछ यही है नीचे वाला फाइनल। हाँ करो ना कॉपी।
किसमें किया है आपने? सेकंड सीजन 5 PM।
आप संभाल रहे हो?
ये मैं से कर रहा हूँ।
ठीक है।
आप वाला बता देना कौन सा जो आपका है ना।
अभी वाले सेशन में APPT बाहर जो
ये वाली
ये 5 बजे का नहीं है अभी जो है
ये मैम वो उन्होंने बनाया ना।
फर्स्ट सेशन अभी है क्या? ऊपर पर इसमें उसमें ना
ये तो कल का है सर। कल का है ना ये तो। मैम को बुला लेते हैं मैम।
अभी थीम 4 है ना?
ये नहीं ये PPT सेकंड है
यही ना, मैंने यही तो किया
हाँ
था।
2:30 PM सेशन। हाँ
वो जब भी करके गए थे वो कहाँ पे किया था उन्होंने भैया? ठीक है आपका हो गया ना?
2:30
कौन सा वाला? ये वाला ही है ना?
मेरा तो ये है। ठीक है
चेक कर लेते हैं, पता चल जाएगा ना।
ठीक है मेरा भी
ठीक है सर।
थर्ड टॉप है ये थर्ड। अभी मेरा नहीं है।
हाँ कोई आपने भी कॉपी किया था, वो कौन सा था?
टॉक्स में था सेकंड सेशन में। टॉक्स में
तो इसमें क्यों कर रहे हो आप?
मुझे नहीं पता ना, मुझे लगा टॉक में होगा।
हाँ पर वो कौन सा
सेकंड सेशन।
हाँ
इको कम रखिए थे। हाँ। हाँ। Good afternoon, everyone. After an engaging set of scientific exchanges throughout the morning, filled with stimulating ideas, diverse perspectives, and thought-provoking discussions, we reconvene with renewed curiosity for our post-lunch session titled Geophysical Insights, Imaging the Earth. This session brings together new age developments from high-resolution subsurface imaging to innovative electromagnetic tools and integrated exploration approaches that are reshaping the way we see beneath the Earth's surface. It is my privilege to welcome our chair, Dr. Dinesh Gupta, retired Director General, Geological Survey of India, a veteran geoscientist whose leadership and contributions have guided numerous national geoscientific programs. I'm equally privileged to have with us our co-chair, Professor S.K. Pal of IIT ISM Dhanbad, an eminent researcher, educator, and applied geophysics expert. May I please request Shri L.K. Khatri, Director, GSI Western Region, to record the proceedings of this session and be our reporter. Thank you, sir. To set the tone for this session, we are honored to begin with the keynote address by Professor S.K. Pal, Associate Professor, Head of Department of Applied Geophysics at IIT ISM Dhanbad. Professor Pal holds a PhD from IIT Kharagpur and MSc Tech from BHU, and his early professional tenure with NHPC equipped him with on-ground expertise in engineering, geological, and geophysical investigations. His research spans an impressive spectrum: satellite remote sensing, image processing, GIS-based modeling, near-surface and environmental geophysics, engineering geophysics, geotechnical modeling, and even archaeological geophysics. With prolific publication record and impactful contributions that integrate geophysical techniques with geospatial technologies, Professor Pal stands as one of the leading voices in India's applied geosciences. His achievements have been nationally recognized with prestigious National Geoscience Award, an accolade that reflects not only scholarly excellence but transformative contributions to the discipline. Today, Dr. Pal will be speaking on advancing geophysical practices beyond conventional boundaries, a topic that promises to expand our understanding of modern geophysical innovation. Please welcome Dr. Pal.
Starting with, I request Dr. Pal to start his presentation. Dr. Pal, please. Thank you very much.
Very good afternoon. Is it okay? Yeah. Very good afternoon. I hope I could make something different, purely application of different case studies that I learned starting from my earlier career from NHPC to the present day. And I really feel privileged to getting opportunity to share the session with renowned geophysicist and the renowned academician. It is really my great privilege. I am thankful to GSI that the topic I have selected that little intentionally to
getting opportunity and to motivate the new different geophysical application, that whatever the different problems, there are so many problems, but it is, I feel it is an art how the geophysical tools can be effectively utilized. So that's what I kept the title like this. So I would be covering, considering the time bound, I am not going to spell out all these things. So this is the first topic I am going to cover, that high resolution 2D electrical resistivity tomography study that has been carried out to monitor the structural health of that our heritage building, IIT ISM Dhanbad, that is rock mechanics lab. Due to natural wear and tear forces and different practical activities that been demonstrated in the rock mechanics lab, that leads some cracks, that is some structural problem in the building, that wall. And that was requested from the administration side to have some non-invasive understanding characterization of the wall, how it is. So that time I don't have any specific tool like that high resolution GPR or any other specific high resolution seismic tools that I could utilize. So only what I feel, that whatever the instruments facility available in the department, that which one could be best utilized. So that all these application that mind, it was first I get that thanks to NHPC, that all the ideas I got, that it is a kind of jugaad technology that I did. So that in the wall that you see that this wall, that about 2.85 that meter, that equal interval of 96 point of 2 centimeter each drilled using a small drilling machine, and that hole was filled with clay and salt using a syringe machine, forcefully pushed into that hole to make the bricks conducting and for injecting of the current for suitable environment. And then we use some nails, small nail inside that, and all the nails are connected serially according to the 96 electrode instrument, C-scale instrument I utilize, that serially, that all 96 that cables were laid out in front of that building, and then all the takeout are serially that connected one by one to each of the nail that were inserted in the respective holes, and then whatever the cracks that been digitized using that yellow dash line that have been used to understanding the corroboration of the resistivity results. That this is the location that of that huge crack that is monitored, identified in the wall. So that have been identified, that how it is extended, what is the width of that affected area, and if any other area apart from that is been visualized surfacially, any other extension, and some other pillars were also studied in the same manner. All, I think, total 8 pillars we identified, and in the 8 pillars we did it same manner and identified all the different structurally disturbed area. Now I am coming to another study, that coal fire is a very serious issues in mainly the eastern Indian coal fields, like that Jhoria coal field and that Raniganj coal fields. So that coal fare mapping is a very challenge to the local people as well as for the industries. So first time, it is my first, I can remember that I started when I joined ISM, that first time I thought that what to do the first research, because I was doing something different in NHPC only for hydroelectric project. So I started with, that was what I remember, one senior professor, Professor P.R. Mohanty. He suggested why you are not thinking for coal fire. Since then, I started to study the literature and the suitable tools I try to identify, and I did. I attempted in different coal mines and identified several that location that are affected and dynamics of coal fire. That these two are magnetic data collected in 2012 and 2014. This is a part of PhD work of one student, and we could able to identify that some high magnetic anomaly zone and low magnetic anomaly zone, and low magnetic anomaly zone inferred to be associated with the coal fire affected, and the high magnetic anomaly zones inferred to be associated with burn and cooled area. And we try to identify and associate the thermal image and the surfacial image to the corresponding anomalies. So that again, we analyze both the magnetic data collected in 2012 and 14 in differently, and we could establish that with the time lapse, that study indicate coal fire front moving upward during 2012 to 14. Then similar study, we analyze different other Euler method, and then we try to corroborate them, their anomaly pattern. And then another site we identified, East Barsoria. That scenario is something different than the Pathodi of earlier site we selected. This site also in 2012 and 14 under the PhD work of my student we conducted, and we see in this area that depth is, that coal fire front is moving downward. So that in two different two different observations we identified, because that one site was that totally filled with the sand and soil to arrest the oxygen supply. If you are arresting the oxygen supply, so coal fire is not getting to move further downward. And if you are not arresting, so it is going, keep on burning. So that is the case happening, that one is going upward movement, another is going downward movement. So for same East Basuria area, we identified one section for ERT study, and ERT study in 2012, that we see that effective coal fire is associated with relatively low resistivity value due to the coal fire and moisture present, and that indicates the relatively low resistivity with reference to the surrounding area. And after the burning out, that area become dry and then crack and void. So that's what after the 2 years time lapse, that whole part is become the high resistive from the low resistive. This is one another study of that Pathodi 2 section we selected, and in the 2 section, 2 parallel lines, we could identify one area totally that burned out, and another is this one is partially burned out. That this is one another study, that combined study of earlier only magnetic, then resistivity. Now we are considering in a Chhatabad colliery that combined study of resistivity, then SP, magnetic, and thermal data. So combined analysis can indicate how the fire front is moving and the fire affected area. This is one another study in the later stage. We conducted magnetic study, resistivity study, and we could correlate their that whatever the fire affected, these are very shallow, these are basically dump area, so that fire not been in the deeper part, in the shallow part, that some overlying local seams are left out, those are in running condition, burning condition. This is another study we conducted long back to understand one area that was very much affected by some unauthorized mining nearby that old abandoned mine. So we could able to identify the extension of how the different unauthorized mining activity were carried out, that G1, G2, G3, G4 are the probable extension of the unauthorized. This is another study recently I conducted with our students for a part of R&D project. That area is affected with, again, some illegal unauthorized mining activities, that magnetic data and then corresponding area magnetic data. We conducted some MSW study and resistivity tomography from the magnetic. We could see some probable extension of the unauthorized mining galleries that have been identified in the surface cut of the abandoned mine. And at the backside of this abandoned mine, there is one ground. On that ground, we conducted some seismic study. In the seismic study, we could able to identify some low velocity area that is probably, we are linking with this low magnetic zone, that is the void. Now coming to another study for the Blackstone quarry. In general, Blackstone quarry is not been much studied geophysically, not been reported. This was we conducted in a part of Rajmahal near that Pachami block. In that area, we conducted magnetic, resistivity, and seismic. Then we could able to identify that high magnetic with the high resistivity and high seismic velocity, that is basically zone with the compact blocks rock. This is another study for bauxite exploration. In general, bauxite is not been much controlled by geology. So these are the pocket deposits, so that bauxite exploration is very challenging. So for that it was requested by Hindalco long past. Then we conducted multiparametric study using magnetic, GPR, resistivity, and seismic. Then we could able to correlate with the low magnetic, high resistivity, and high seismic velocity with some specific something distinct reflection point in the radarogram as bauxite boulders. This is another study I conducted as a part of that. This is a project under SJVN. That in SJVN there was some challenge to have the resistivity study for mapping the basement under the river bed. So there was challenge for us without that specified resistivity cables that are specially designed to carry out the study in the water. So that was not available that time with us. So I conducted some study with Jugaad. That again we lay out the ERT cable on the bank of the river, and then that each take out we connect with flexible cable, and at the end of the cable put one that metallic screw and another stone, and then with a stick we put in the river bed. And in that way we conducted the study, and then by considering all parallel ERT lines, we could able to understand the depth-wise distributive variation, and at a greater depth, we could, that at a depth of this particular homogeneous distributive variation inferred to be the basement rock of that area. This is another study for the dam seepage, that at the bench of the earthen dam, that at 3 different bench we conducted distributive study, and from the distributive study we could able to establish there was some high that water seepage, that pockets and their probable extension we could able to understand. That was the study conducted at Durgavati Dam in Kaimur district, Bihar. And another study conducted in that Sambalpur, Odisha, Talavera coal mine, that Hirakund, that reservoir in between. So there was an issue with the seepage. That seepage is visible, and that was challenged to identify the seepage, path. So by conducting parallel lines of distributive tomography and then SP, we could able to identify the location of low distributive patch, and that we could able to correlate with the seepage location, inferred to be the seepage path. Now coming to something different that very rarely been utilized, that I conducted some resistivity, GPR, magnetic, seismic, comprehensive study in parts of that Birbhum, Siuri, West Bengal, that is the area with a myth of Bakasur. There was a demon Bakasur, and then there was a fight between the demon Bakasur and the Bhima in that area, and that land is known as the Osurdenga. And in that area, that was the left for several years, and in that area we conducted that geophysical study to have the understanding of the ancient historical features. And we could able to identify certain patch of high resistivity and some specific pattern of radarogram and high magnetic anomaly. And those basically, when we identify the depth and geometry, the archaeology expert from the Calcutta University, he told his disagree that anomaly and depth and geometry may not be acceptable as per the archaeological context. Then I told that is very difficult, it is acceptable or not, but whatever the data I have collected, and it is, I can't deny that. And afterward, he accepted it with the for some excavation he conducted, and at that specific depth that have been identified in resistivity tomography, in that depth they identified one patch of potteries. Okay, so that study still is going on. This is another study we conducted recently. It was a real challenge for me for that Tilpara barrage over the Moirakhi river in part of West Bengal. So that barrage was basically, what I remember, 75 years old. Okay, and since then there was no any health monitoring or retrofitting not been done. And recently, due to probably some unauthorized sand mining in the downstream, that river that become disturbed, and due to that, whatever the toe protection that also disturbed, and then whatever the seed piles are there, from the beneath of the seed piles, all that sand and soil that naturally been eroded, and some voids created, and due to that, initially in the year 2023, after the flood, 2024, there was some symptoms that barrage is going to facing some issues. Okay, and then they conducted for some non-invasive characterization. Then subsequently, we conducted detailed study using seismic, and also we proposed some microgravity to that, but due to GPR, microgravity, and seismic. But finally, that seismic and that GPR gives the very satisfactory result, and it is really, I feel it is a almost 100% perfectly matched with the anomaly actually in the field. Okay, so this is the layout we conducted on the on the foot of the barrage. So this is the alignment of the instruments and data were collected, and this section indicate the how the data earlier was, and this low velocity zone that was identified from the initial study in before the monsoon of this year 2025, and we identified our concern that area is to be taken care. But that was not been, they drilled in all the but they could not identify any disturbed or any hole in that area, but we identified our concern with the low velocity patch in that area. And since it was not been identified any hole, so they did not put any filling or any other treatment they conducted. But after that, due to heavy flood and heavy water discharge, that part get damaged, and then afterward they filled with some concrete, and then we conducted again study, and we see that that area, that velocity in terms of velocity increased. Okay, so this side indicate the study conducted in 2025 May, and in 25 May we identified some relatively low velocity that loose material in terms of radiogram reflection and in terms of low velocity patch that indicate the red zone, and that get damaged after the heavy flood, and then again they filled with a concrete, and then we again collected the data, and that with the concrete filling that completely identified with the velocity distribution diagram. And that we continued for total 30 segments of the barrage. So whatever the void been identified, they drill and they cross-check with the data, and that match almost 100%. This is the one photograph after the drill hole, and this is the video of that segment, and it was get damaged due to the improper impartial filling, and then again after that September, that partial damage, they fill it that area, and we conducted the study, and it indicates some good amount in velocity increase. Okay, this is another study I conducted for the structural health monitoring across that NH2 over the underground mining gallery, and for that we conducted that resistivity tomography in both sides of the NH. That was also a great challenge for us. We conducted that. It was very difficult to insert the electrode, so we used heavy drilling machine to put a hole, and inside the hole we put the bentonite salt, and then we collected the data, and we could able to identify some low resistivity patch that could be associated. This one we identified as may be associated with jointed, fractured, weathered formation that may be linked with the underlying gallery identified in the NH segments as per the resistivity tomography. But afterward we conducted again seismic study that seismic study, that seismic data acquisition, also very great challenge. So we stopped the total traffic in the night, and we collected the data from night 1 p.m. to 4 p.m. and we collected the data, noise-free data, and from that data we could identify that all the high-resolution features, starting from the overlying, that aggregate, road aggregate, then compacted aggregate, and then sandstone, and then also there is one local coal seam at about 10 to 12 meter depth that match with the your litholog available of that area, and that also match with the GPR. But in some, this is the reflected in the GPR with the coal, and then we could able to identify some relatively heterogeneous low velocity around the, that gallery across the road. But in general, though we identified that relatively heterogeneous low velocity zone that can be linked with the gallery, but in generally that considering all study, including the radarogram, that does not indicate any instability or that any heterogeneity that can cause a serious concern for the highway. Okay, so with this, I complete now. I would be happy to interact.
Multiple case studies presented by Dr. Pal, starting from vertical resistivity to all. So several interesting case studies. I selected few questions. Sir, one question.
Sure.
Sir, how do you operate upward continuation technique to potential field data, SP data?
Basically, that it is applicable as the potential field technique that like the gravity or magnetic, that it is a signal, nothing but it is a signal. That technique can be applicable to any data. It is a upward continuation, it is a signal processing, that signal enhancement technique. So we considered based on the in general we consider upward continuation height based on the RAPS, that wherever the average boundary of the that horizontal different layered strata. So to that height we consider the upward height in general.
You have prepared any control file for this?
What?
Control file.
Control file?
Going to apply upward continuation. You have submitted some control file for executing that upward continuation.
Yes, yes.
You have adapted this technique to SP data.
Yes.
How you have prepared?
Basically, I adapted simply as a potential field data because SP is also a potential field data. Considering that, I adapted the whatever the concept. Just the height we consider, considering the RAPS, radial average power spectral data.
Any more questions? If not, then we will go to next speaker.
Thank you. Only that my request to the geoscience community, I feel that geophysics is a tool like that we do in that different pathology or X-ray or radiology for the medical science. So there are a lot of scope that can be done. So if we apply properly, knowing the limitation, then it can be utilized in different aspects, starting from the archaeology to agriculture to different day-to-day activity to addressing the social need. That social need, mainly the one is the geotechnical or construction of the building, how building is safe or not, and then the groundwater. So, so that is my only that request, that if we try to address the common man society need, then it would be more useful for the everyone. Thank you.
Coming to next paper, Kimberlite pathways. Kimberlite pathways in Vajra Group, Kimberlite field of Eastern Hall-1 Craton, India, geophysical approach, RT Singh and Bangalore. Are there? Why you have said second author is there? This is injustice to science. I'm sorry. And you are there, second author, any author can do presentation. Anyway, next we go to third paper. Tab to go, a backpack mounted transient electromagnetic system for fast and efficient subsurface mapping. Deep More, Epson Ocon, and Rizom. There. Friends, it can be a very interesting paper because the topic transient electromagnetic. In India, as a professional geologist, not much has been done at field level. Only theoretical level we have done. Now GSI recently has started it. So I request, please be attentive. This will be a very good presentation. Thank you. I welcome you.
Thank you. Yes, I'm going to talk about affordable and efficient TEM geoscanners provided by the company called TEM Company. We are a Danish international company with a very worldwide presence. We offer easy-to-use system for subsurface imaging for non-experts. Innovation, responsibility, and quality are our core values. Okay, just a little history. Aarhus University finished developing TTEM. T stands for TOAD, TEM, in 2015, and in 2020 they made a spin-out company. They called it Geo Instruments. Then in 2023 Grundfos was buying 25% of us, and that gave us a lot of money, and it gave us opportunity to develop new systems. And today we are more than 30 people with an ambitious research and development, production, and a sales program. We aim to define the future of subsurface mapping by setting the standard for integrated hardware-software solutions. With intuitive geoscanners, we transform complex water and mineral exploration into simple, scalable insights that fuel sustainable growth. So the technology TEM stands for transient electromagnetic. We have made integrated hardware and software for subsurface imaging. All our instrument is operated by a phone, a tablet, and you can even put it on a PC. Okay, just briefly, what is the method, right? So you have a transmitter coil and you have a receiver coil, and the red is the transmitter coil. So you start sending current, so you have a steady current which is transmitted into the transmitter loop and creating a primary magnetic field. Next step is to shut it off and induce inductive current in the subsurface, and then the inductive current will create secondary magnetic field, which is measured in the receiver coil. This is a central loop system, and you can also make it offset, so you can have the receiver and the transmitter next to each other, but I'll show that later. So what do you get? You get this curve, which is dBdt as a function of time, and then you do an inversion, and you end up with a model with different layers, with different resistivities, and they can then be translated into geology. Okay, so this is the family product we have. So we have the STEM, which make single site soundings. and you can use different coils. Then we have the TTEM, our most advanced system, where you are driving continuously with a speed of like 20 kilometer per hour, and you can have a sounding for every 10 meter. So you can really cover a large area in one day. I'll go to Tem2Go, which we developed because there was a demand for accessing places where you couldn't go, but you still wanted to measure continuously. So we have two systems measuring continuously, and we have two which is stationary. And there was a demand for XTEM, so they wanted to go really deep, so that's why XTEM was developed. Okay, so this is the STEM, and it comes with three. You can either send 5 amp, 10 amp, or 20 amp, and it comes with different coil configuration. So the three upper one, this is the central loop configuration, 20 by 20 meter, 40 by 40, or 80 by 80. And of course, this takes a little bit of time to lay out the coils and then roll it in. Normally we measure for like 2 minutes. And then we also have this system called the profiler, which is fixed coils. So you can set it down, measure for 30 seconds, lift it up, move, and take another measurement. So it's like semi-fast. It's not continuously, but it's faster than doing the central loop configuration. So this is the Tem2Go system, and the distance between the two people is around 15 meters. The distance is measured and put into the data while they're walking. And on the app, I'll show you that later, you get real-time inversion, so you can see what you're measuring while you're walking. This is the applications it's been used for so far. So it's managed aquifer recharge, it's fractures hard rock, it's mapping groundwater, exploring rivers, saltwater, well siting, pollution, raw materials, weather bedrock, and permafrost. So now I'll talk a little bit about the XTEM. So the vision was to develop a TEM system for very cost-effective 3D subsurface mapping using the state-of-art electronics. The ambition is to go to 1,000 meter plus, being able to dense coverage a large area, and it should be easy mobilization and field operation. And like our other system, it's a wireless control of the device, and you can use any phone, Android or iPhone. So the XTEM system is similar to the other. We have a transmitter loop, we have receivers, but with this system you can use multiple receivers, so you're sending the current in one loop, and then you can go around measuring with other receiver coils. So you can make central loop or offset. The field operation, like the other, is transmit in the transmitter coil. You use one or more receivers to record the DBDT, and you can measure both central and offset using the phone. What does the system contains of? So it's a transmitter, the two yellow boxes, it's a receiver, and then a receiver coil. There's two options with the specs that you can see there. And this is just to show you that we calibrate all our system at the national test site in Denmark, which is the same test site SkyTEM is using. And what you're seeing here is the blue is the reference response, and the red is the recorded data, and they fit nicely. This is an example here in India, where they used the XTEM, and they were able to go down to 700 meter depth of investigation. So the XTEM configuration Either it's 40 by 40, or it's 80 by 80, or it's 200 by 200 meter transmitter loop. There's no cable between the transmitter and the receiver unit, so you save that weight. And the TX and the RX are synchronized by a GPS within 20 nanoseconds. And this one is 9 kilo, and the receiver is 5 kilo. So the most of the weight is actually the transmitter loop. Yeah, I talked about this. This is how we collect the data. So we use a phone, and you actually get, here you can see if you have GPS signal, you can see what current you're sending. You get real-time inversion. So like if you do Tim to go, while you walk, you add each measurement and can see your data and your inversion while you're walking and making a decision whether you want to continue in one direction or another. Okay, so just a summary. So we have 4 families. 2 was measuring continuously, and 2 was single-site sounding. All of them are dual-mode systems capturing shallow and deep information simultaneously. It's like you have to choose. If you make smaller transmitter loop, you can make higher production. But if you want to look deeper, you need to have larger transmitter loops. And just to tell about the XTEM, it's a very lightweight transmitter system, and we have chosen to have a generator using as the power system instead of like 6 batteries of 20 kilos. Then you have to carry 120 kilos. So it's a very lightweight system, and we expect it to go down to 1,000 meter plus. That's it.
Thank you very much. Any questions, please?
What is the resolution at 700 meters?
Yeah, that's a good question. Actually, we have invented a software which where you can put in your model, your expected model, so the thickness of the layer and the resistivity of the layer, and then put it in and see how the response is. So I would actually recommend. I think it will come out very shortly, and I think it's going to be open source, so you can have it and check whether whatever your target is. But like we are measuring resistivity layers, so whatever you're looking for need a contrast between the resistivities, right?
Because it can have very serious advantage in case of deep-seated tunnels today being planned for highway, part of highway or hydro tunnels, which are more than 500 meters below the ground. If it can be of some use in investigation, it is good, we can try it, but I doubt what will be the resolution.
I would like to see how thick your layer is and the resistivity of what you expect the resistivity to be, and then we can see. So like if you're looking for 10 meter and 500 meter depth, the answer is no. It's like it have to have a certain volume.
It may not be 10 meter, 50 meter, 30 meter. It may not be 10 meter. We are not expecting 10 meter at 700 meter depth.
Okay, good.
But
Thank you.
at least at some 50 meter, 40 meter thick bands, that we should be able to justify. That is quite reliably for at the investigation stage. If it is so, then we can use it.
Yeah. Please give us the model you expect, and we can show you how our systems respond to the model you want to look to find.
Okay, we will see.
How you will give the parameters for 700?
No.
Where you will get? Either you
No.
Once you build the system becomes not required.
Yes. Because that I will know only after excavation.
Physical methodology. Let it be gravity assumption, because we have got certain view, 700 meter, what geology, lithology is existing, based on that what is expected density, contrast, or different parameters that we need to give.
But, but in Denmark, we have recorded wells for 100 years, and we have few wells going down to 1,000 meters, right? So you should, I hope you have
No.
some deep wells, no?
But there is difference between your lithology and Indian conditions.
I'm just saying, but
We are concerned with the Himalayan geology mostly, and where the variations are too often. Yes. Yes.
Then conducting to very fragile rock to very hard rock. So, is the system good enough to?
well, can you tell me the resistivity of the layers and the thickness? Then I can give you an answer, right?
That, is it any soft rock or conducting? Is it applicable to soft rock or alluvial, not alluvial, any soft rock?
Okay, so the electromagnetic methods measure resistivity, like ERT, ERT. So have you been using ERT in these conditions and getting the resistivity? No.
That if that in general geological success and that contrast is relatively less, in that case, will it be effective?
Yeah. If the contrast is too little, it will probably not be possible, right?
No, but in ERT we are not claiming 700 meters.
You see, he was telling 1,000 meter, 1,000 plus. He said it's a big challenge. I will be happy. I will give my email ID to share any successful case study of any part of the globe.
Yes.
In your country, 100 meter, 1,000 meter plus, any successful case study that has been verified by different alternative intrusive methods.
But
I'll be happy to go through that study.
Yes, sir.
But of course it depends on geology and noise sources.
Naturally, ideal geological conditions,
Yeah.
Sir, I want to, you are having 4 systems and different systems. But your general statement is that 1,000 meter penetration.
Okay.
I think it is not same for all 4.
No. I think I maybe was a little bit too fast.
Is there any data?
Sorry, I think I'm taking out that slide. I had a slide telling how deep the different methods. Yeah, it's only X-Temp, this one is maybe 150, 200, depending on if you buy the S-Temp 20.
So you are talking about X-Temp.
And this one also.
But there is one question. If it encountered the water table, what will happen then?
100 meter.
Water table.
I think.
Suppose my Siberia falls in a location where water table is very near to the surface.
I think the 3 first will work.
Can we go beyond that?
Beyond 100?
Beyond the aquifer.
Beyond the aquifer, we can go, I think.
Yeah. So again, it's a question of the resistivity of the layer.
As Dr. Pal said, clay or mud.
Yeah. If you have a high resistivity layer with clay underneath, you will see it.
It is overburden.
Yeah.
There is a loose sediment covered.
Yeah.
There, this system will be difficult to apply. It's not it.
I'm not sure I understand you. So what's the question?
If there is a sediment layer,
Yeah.
and naturally there will be water in sediment layer.
Yeah.
We cannot penetrate below that.
Yeah. If you have a sedimentary layer
Yes.
with, like, say, a ohm meter of 100 ohm meter, and then you have a clay layer beneath, that's a really good target for the temp.
So we'll be going for hard rock. hard rock lying below the
But if you have high resistivities and high resistivities below, it's not so easy.
the resistivity, when this sediment column will contain water and will be low resistive, then all the lines of force will be directed towards along that area. And there will be no penetration down. So you cannot go down with this system.
But like I said before, please give us the information of the layers and the thickness and the resistivity, and we can tell you whether it's possible or not.
Okay, thank you very much. And join me in giving a big hand to Dr. Soren Goyal.
Thank you.
I invite next paper, delineation of surface potential geometrical delineation using integrated geological approach in parts of non-verified belt, Haryana, India, case study 2532. That 2532 क्या मतलब है साहब इसका? शोभे साहब?
Code, this is code, sir.
Case study 2532 is a mistake or what?
It is a theme code, sir. At least. Yes, sir. A very good afternoon, respected dignitaries and other geoscientists. My presentation is focused on delineation of subsurface potential zone using integrated geophysical approach in the part of North Delhi Fault Belt. My presentation will follow the following sequence. What are the motivation behind this study? What are the objectives? What is the study area? And what are the methodology? And what are the sequence of methodologies we have adopted in this study? And what is the outcome? And finally, there is a future scope from this study. So as we well know that this Aravalli-Delhi Fault Belt is a very complex geological or geotectonic system which has attracted many geoscientists to go for geotectonic studies as well as in the direction of mineral exploration. And for example, this Copper Khatri Belt and that is Alwar Sub-Basin that attracted many geoscientists to work in this field. So we thought that I am from northern region, so it's just in continuation to the Rajasthan. So to north of this Copper Khatri Belt, we have identified one area of 5 toposheets where NGPM data was available. So we compiled that NGPM data and identified some potential zone for further exploration. So the main geological domain in this study area that is Ajabgah and Alwar group, which has given a very interesting geological domain for mineralization point of view. So from the compilation of gravity data, we have demarcated many linear features in terms of inferred contacts and many high and low gravity zones, which is very well corroborated with bipolar anomalies, as you can see in the right side. So we have interpreted these things due to the subsurface geological changes or due to some structural changes. So these lineaments, whatever we have demarcated are magnetic anomaly, we have further integrated with the available geological data, that is structural or some lithological data, and identified a potential zone for further exploration. So from the potential field data, we have to do some data enhancement technique for better interpretation. So first we have computed this regional data using low pass filter that cutoff wavelength we have expected from, we have calculated from radial power spectra of gravity data and magnetic data, and we can see one very clear-cut northeast-southwest linear feature, which is in the depth also, and very interesting. For mineralization of point of view, our main interest on the residual data. So we can see many northeast-southwest, even southwest-northeast features, which are further interesting for further exploration. So, and we have also computed the depth range of these causative sources from the gravity data.
And for ground magnetic, we don't have data for two toposite, so we have consulted aeromagnetic data, which is very similar to the ground magnetic data. So wherever the ground magnetic was not available, we have considered this aeromagnetic data. That is similar, bipolar nature. We can northeast, southwest, we can many bipolar nature we can see from the map. So based on this NGPM data as well as other geoscientific data, we prepared mineral prospectivity map. That is not in the scope of this study, but we identified many potential blocks for further exploration. Among them, one is the Ghatasir block, where we did the detailed geophysical exploration, geophysical survey. So we did all the multi-parametric survey, that is gravity, magnetic, and IP, resistivity, as well as SP. So this is the layout map of detailed geophysical survey, where we took the traverse interval at 200 meters and strike direction as per the general strike of the geological domain. So we can see this is the Vogel gravity map of the detailed survey. So we can see one, contact which is along the strike of the geological domain. So, and we have one high zone, and we have contact where we are getting moderate to low magnetic anomaly in the center, and which is well collaborated with the low SP. And at the same, in the same direction, we are getting high chargeability and low resistivity. So that is kind of, we can say, it is an integrated outcome which give in the direction of the mineralization of point of view. Now, in geophysics, we have identified subzone. Now, most important is what is the depth of this causative source. So we have done dipole-dipole survey along two traverses, and we have got high chargeability around 30 in the depth of from 70 to 125 meter. Along both the traverses, almost from 57 to 125 meter, and from 70 to 125 meter from both the locations. And we also did Euler depth solution of gravity and data, and most of the solution are ranges from 100 to 250 or 300 meter. And another depth technique, that is radial power spectra, we have computed from gravity and magnetic data. Both, one is from 90 to 270, another is 80 from 200, and other that is Sajal 9085 method. From the resistivity data, we can compute depth of that anomaly. So from that also, we are getting for different types of body. It may be a spherical, cube, cylindrical, or parallelopiped. So I took two profile data from resistivity, and as I have already marked this LR1 and LR2. Two profile I took, and depth was ranges in the range of from 70 to 120 meter. So from depth analysis of multi-geophysical techniques, the depth ranges from 60 to 300 or so. So we have suggested some anomalous point for further exploration or further correlation with the geological data, then may go for drilling as well. So accordingly, after integration, one scout borehole was done at AN1, anomaly point 1, and which is very near to old working. One old working is there. So it is always go from known to unknown, although we are getting more chargeability or more anomaly point in the south, but it is always go to from known to unknown. So other, other domain expert decided that scout borehole should be done near to the old working. So, and we got good result. You can see from geophysical logging, as we suggested, the depth range from 70 to 300 meter, and you can see conductive zone we are getting from 80 to 200 something with high chargeability value, which is a very good, collaboration or with validation of our result. So this is the outcome. And in scout borehole from outcrops, scout borehole from geochemical analysis, also some mineralization were reported at the same depth. So that is the outcome of our study. So we can say that now the time for integration, all the domain experts from geology, geophysics, or geochemistry sit together to identify the potential zones for further exploration. This is point one. And that is for detailed investigation in terms of dimension of the body, in terms of width and depth, we have to go for multi-parametric geophysical survey. Third point is we have demonstrated in the Ghat area, our results have demonstrated that it has been successful in terms of delineation of potential zone, in terms of depth, or in terms of location. And so we can conclude that our study has given a right path for identification of potential zone using multi-parametric geophysical survey. Thank you very much.
Any questions, please?
Mr. Bharma, it's a good presentation. You have done depth distribution from resistivity.
Yes, yes, sir.
But not from any gravity or magnetic data. It is there.
Yeah, I did GMC's modeling from gravity and magnetic that I have not shown, but it is in that depth range.
Gravity modeling is done.
Using GMCs I did. GMCs. It is in the report, sir. Yes, sir.
It is in the report.
Yes, sir.
Not sure.
Yes, sir.
But actually the whole objective of geophysical survey is to reduce the
Actually, sorry, sir.
give the proper location of the drill. So in that case, you need to know the 3D disposition of the body.
As per,
You cannot give the drilling.
no, that is, we have not suggested drilling point. We have suggested anomaly point.
Understood. But the whole objective of geophysical survey is to give the reduce the drilling cost.
No, that is.
Give the drilling point properly.
So suppose, sir, in an area we are giving some anomalous point. That is ultimately reducing reducing the possibility or probability of selecting the well location. Yes, sir.
Still, the gravity anomaly itself does not say that this is the body.
That is there, but that gravity data you can see we are getting gradient, but in the modeling we were getting the structural features, not exactly in the direction of mineralization of point of view. That is, this is copper mineralization. We can't say like that. So that's yes, sir.
Next gen
Yes, sir. Yes, sir.
geophysical work should address this.
Yes, sir.
Thank you.
But as I could understand, based on initial gravity and magnetic data,
Yes, sir.
you planned a small block with detailed geophysics and
Yes.
showing all the images.
Yes, sir.
And based on all the images, borehole has been proposed.
Yes, sir.
It is immaterial. GSI has done the borehole. You propose or me, I propose that is immaterial.
Yes, sir.
And based on the data, there is no any other geological control in the area which have, based on that borehole has been given.
Another interesting point is that, sir, I can show this map. Yeah, this one. We have only exposure near to the old one. The anomaly wherever we are getting, that is from geophysics.
That's what I am saying. So borehole has been planned exclusively based on geophysics work, and that is. You told the minerals, I would have been happy to see the borehole geological section.
Oh, that is.
So that is the main outcome of your work.
That is not in the scope of this presentation, but I can show. This is, I have picked up from the geological aspect.
What is the scope? You are doing presentation, you are the Malik author of this paper. You can do anything. Who stops you in the section? That gives a clear picture. आपका जो question था ना?
जी sir. This is you can see. Is you can based on the amount of mineralization 6 identified zones from 70 to 91 zones.
What type of mineralization that you need to mention?
That is there, sir.
Zinc.
For pyrite, chalcopyrite, and other things. Sulfide mineralization in the fauna designated. Pyrite and pyrite.
So your gaps are matching.
Of chalcopyrite.
Gaps or mineral intersection is matching with the gaps
Depth.
you are proposed.
Yes, sir.
Calculated based on your data.
Yes, sir.
Right. Okay. Thank you. Any more question?
Presentation is that the zone demarcation plus estimation of depth by different technique. So, and that was 100% exactly the mineralization was encountered at that depth. And we also gave the last depth, that is 300 meter vertical, and the drilling was done up to 450, around 450 inclined. And that was successful. Although the mineralization, the mostly pyrite content was more, but pyrite, chalcopyrite and bornite, major content was that. So from geophysical point of view, the sulfide mineralization was encountered, and that was the successful in that view.
I appreciate Chaudhary Sahab. It's a very successful case study. But at the same time, our objective of identifying a vital breakthrough in discovering new deposits. So one borehole doesn't serve the purpose. The whole map should be fixed to plan and integrated in totality the several boreholes and complete the area. That is the objective.
Sir, we have suggested two another test borehole, but that was not done anyhow.
Okay, thank you very much, sir, for my presentation. Please join me in giving big hand. High resolution Hall-1 transient electromagnetic survey, a DSS tool for recreating aquifer framework on sustainable management of groundwater flow, pinpointing of potential groundwater and Mars sites in Goa, Pali, Rajasthan, India, Singa, Sunita Devi, and Veer Babu, Priya Kumar, Subhasan. ये अंजना पेपर?
नहीं सर, CGWB पेपर सर KP Singh sir was again. Yeah, yes, sir, he is from there. Because we have a collaboration with NGRA. So, oh yes, sir. Very good afternoon to the august gathering. I am going to present the paper on Hall-1, high resolution Hall-1 transient electromagnetic survey, a decision support system for tool for recreating the aquifer framework and the sustainable management of groundwater through pinpointing the potential groundwater sites and the managed aquifer sites in the Rohat block of Pali district, Rajasthan. Sir, this being in a totally entirely project away from the research orientation to the service to the society. So I will just tell what is the necessity of this very project and how we dealt with this project. In this project, we were envisaged to be covered 400,000 square kilometer of area in two phases. In the first phase, we covered 1 lakh square kilometer in the parts of Rajasthan, Gujarat, and Haryana. And around 96,000 square kilometer area was covered, and the 40,000 kilometer of Hall-1 TEM survey was carried out, sir. The main necessity of this Hall-1 survey was that in the northwest India, we have around 12% of area with around 8 crore of the populations, where the water levels are very deep, with the high rate of extraction. With the 65% of the groundwater assessment unit, they are overexploited here. And these areas also have the low and erratic rainfall. With the potential groundwater zones, they are very deep, mostly in the range of 80 meter and beyond. And there the groundwater quality is also there. Means we have both the problem, groundwater quantity as well as the groundwater quality in this semi-arid area of our northwest India. The complex hydrogeology also makes our groundwater exploration extraction very tough, because the sandstone, limestone, metamorphic granite and other granite formation, they have the secondary porosity, and to identify, pinpoint them is a difficult affair. So the geophysics comes here, and beside the groundwater geophysics, this Hall-1 surveys has really helped us. And this will also supplement our NACUM study, National Aquifer Mapping Studies, which the Central Groundwater Board is carrying out, by supplementing with a deeper, high resolution and denser data. So in this, the time surveys, everybody, sir, know the basic principle that current is flowing in the loop. Okay, thank you. This is the system specifications. We have used the SkyTem 312 survey system. And the main thing is that this is the dual moment system where we can identify the formations from the shallow depths as well as the deeper depths. And the transmitter current is 5 ampere, and the maximum current flows is the 120 ampere. And the NIA, which is the controlling factor, is the 3000 NIA for the shallow delineations, and 5 lakh NIA for the deeper resolutions. Now coming to the methodology, sir. Here, not only the airborne, heliborne surveys we have carried out the surface geophysical surveys also, followed by drilling and geophysical logging and pumping tests. In heliborne survey, we have gathered TEM as well as the magnetic data. On ground, we have done ERT surveys, EVRI, electrovoltic resistivity imaging, and then the TEM survey, sir. In this, the main sequence is pre-heliborne survey. We have gathered the data, ERT and ground term data was acquired. Then the heliborne survey was carried out. And on those points where there was no data due to the heliborne, the ERT or TEM data was gathered. And then the post-heliborne surveys were carried out where there was noise on this data. And processing of the heliborne survey was carried out. Then the data integration was done, heliborne data, ground geophysical data, and our already drilled CGWB's wells were incorporated, and then processing and inversion was carried out, and the interpretation was done, and ultimately its translation of the data to its aquifer informations. And then on the basis of all this processing and inversions, we carried out and identified the managed aquifer recharge sites and the potential groundwater drilling sites, sir. This is our raw data, and by using the RS Workbench softwares, we processed it and identified the all the noise were removed, sir. Now coming to the study area, this is the Rohat blocks falls in the Pali, western part of the Pali district with an area of 1,356 square kilometer. Now all this, our exploration study was on a block level, so that the information from district to block and then to the basic assessment unit of village was, we are able to provide our groundwater information to the local villager or the farmer, sir. The geology of this block varies from thin alluvial cover to sub-recent, post-deluge granite, and Ehrenpur granite and Malani rhyolites were there, metamorphic rock of Delhi group were there. And the water level ranges from 1.4 to 11 meter BGL, sir. And the EC values were from 1,915 to 32,880 microsiemens per centimeter. Sir, this is the geology of the area. This comprises of our Ehrenpur granite and Pune group and this thing. And this part, the western part, comprises of the alluvium. So in simple terms, we can say this is the western part comprises of the soft and alluvium, and the eastern part and northeastern part comprises of the hard rock areas. So we have done the analysis of all the heliborne flight lines on the village level, sir. The village boundary, according to that, depending upon the flight line section which is passing through a particular village, all the information was gathered and interpreted on the basis of these resistivities, TEM values, sir. In just like we can see in the Bithu village, CD profile was there, and from the CD profile, all the temp soundings were interpreted, and subsequently interpretations were made for the drilling sites and where the manual aquifer recharge can be done. And we have given all the information along with the lat long, where we can do the extraction and what is the depth range, what is the quality of the groundwater which is going to be extracted, and if managed aquifer recharge is recommended there or not. As in the upper part, we can see it is all comprising of the low resistivity values, means the saline water is there. Again, putting the managed aquifer recharge there will make the fresh water saline, so we have not recommended any managed aquifer recharge there, sir. Then coming to the next example, this Gram Panchayat location is at the eastern part, sir, so which clearly indicates that at a certain depth of 20 to 15 meters afterward, we have a high resistivity values, which clearly indicates the high rock formations, and they corroborates with our earlier geological maps, sir. So all these wells and where the locations of potential drilling site and marsh sites, they are given along with their depth range and the type of groundwater quality. Like this, for each and every block, then coming to the Gram Panchayat level, we have identified these locations. And the limitation of, as sir was saying, when there is a water at the shallow depth, the water with the brackish or saline quality will reduce the depth of investigation, sir. So when I will show you the mean resistivity map, sir, there that thing will be clear. We have a reduction in the depth of investigation in the western parts, whereas we have a deeper depth of investigation in the eastern, northeastern parts, sir. So this is the mean resistivity map of 10 to 20 meter BGL, 20 to 30, 30 to 40. So you can clearly see the high resistivity values on the eastern side, sir, whereas the low resistivity values, they are coming on the 50 to 60, 60 to 70, 70 to 80, like that. And after a certain point, you can see, sir, there is all blue, low resistivity values, which is, we can say, they are not very saline formations are there. And depending upon all the locations we have identified and pinpointed, selected those sites where the potential groundwater zones are there and where the managed aquifer recharge can be done. So this map is prepared, and then so in summary, we can say we have identified 93 borehole sites and 21 dugwell sites where we can extract the water, and 23 recharge shafts we have recommended, sir. And we have given the less sites because at shallow depths, the saline water is there in that road block. And deep drilling sites have been recommended with the cement sealing. Deep isolators fractures at Chetalu, Bhitu, Artia sites, we have identified in the depth range of 80 and 150 meters, sir. And the local groundwater conservations or the harvesting schemes, it has been recommended, sir. We have not recommended or encouraged going for managed aquifer recharge here. And we have found a good corroboration between the already existing lithologs of our boreholes and the Hall-1 cross-section profile which we have prepared, sir. And we have given the volume of data to its value and the science to the society, sir. Thank you, sir.
Any questions, please? It is a burning topic, groundwater availability at deeper level, especially Rajasthan is a luxury. So if they are able to identify the deeper level aquifers, though shallow level is saline.
Saline, yes, sir.
It's a challenge because NGRI has developed a software, I am aware, that with that software, which otherwise electromagnetic survey beyond
200 meters.
saline water doesn't penetrate in general.
You have very low resistivity.
Yeah,
is all.
Could you verify these fresh water zones given at that level?
Yes, sir. Sir, as per previous data also, they are also matching with us. They are our Hall-1 results. And even for the validation of this Hall-1 data, we have drilled 22 validation program, and all they were matching 85 to 95% with respect to the groundwater quality, depth of their occurrence, and the formation wise, sir.
It's a good case study. I appreciate, because though GSI doesn't have the groundwater, but in general as a geophysics, this is a very interesting case study.
You have that blue dots are the drilling location for proposed.
Yes, sir. These are the proposed drilling locations where we have got.
What would be the optimized distance between two? Because if we extract or put a drill hole.
Sir, if the discharge is less, we will say they should be far apart. If the discharge is high, means 20 LPS or even more.
Is there any guideline for, say, for
Yes, sir.
extraction of water for
Yes.
our
As I said, guidelines.
for agriculture purpose, for domestic purpose, what would be the distance between two?
Right, sir. Sir, depending upon the discharge, their type of formations, if the alluvial areas is there, the discharge will be definitely be high, so the wells can be at a slightly closer distance, so 300 meter or so. But once we come to the hard rock area, discharge is less. Means basic concept is that their cone of depression should not interact.
Yes.
If they intersect, means one or other well will be at loss. So we have to keep that cone of depression in mind. Depending on that's what I'm saying, sir, depending on the geology and the discharge, we have to have optimize that thing. And depending.
Possibility for groundwater harvesting for recharge are also being analyzed in substitute to that.
So this implementation of this program, these sites validation is in progress, sir. Because drilling we have done, for recharge purpose, we have to depend on the state agencies.
Yes,
so
we have to extract for the society need.
The society need.
But at the same time, whatever the runoff water, if we could be able to infiltrate them at least a few percent, then that balance, it would be water budget would be better.
Right, definitely, sir. But thing is that your initiative, my initiative, all are sporadic. So the impact is not visible at very high, yes. If all the efforts are concentrated in a one watershed, definitely next year we might have a good results. But in 7 watersheds, we are doing different interventions. So the total result or the impact may take a longer time, sir. Right, sir. Yes.
Not only the policy awareness, it is to the homeowner also important.
Just one point.
Yes, sir.
I never found out my aquifer. Broadly, you know the top layer, you know the bottom layer too. Is there any mechanism to find out the water resources, amount of water resources, knowing the porosity and other things, metrics?
Sir, simply yes, by sir, estimation we are doing, the groundwater estimation we are doing, resources we are doing, but everything we are calculating for specific yield into thickness of the aquifer, so that we can know the volume. Into the area we are doing the volume metric estimate. Yes, sir. Now, yes, sir. We are doing, sir, resource estimation of all of us.
The basic objective of this investigation to give the potential volume of water available in that.
Yes, sir, that area.
It will be very useful in the near future for the civilization.
Thank you, sir.
Okay, friends, if no more questions, please join me in giving a big hand to APC. Thank you very much. Now we have the next paper. High resolution transient electromagnetic survey for near surface mineral exploration. George Street, Andrew Duncan.
Namaste. Thank you, Mr. Chairman. In In the 1990s, I was involved in a big groundwater project in Orissa State and we did a lot of follow-up of airborne geophysics at that time using transient electromagnetic systems. One of the things I learned very clearly from that exercise was that there was lots of limitations to using transient electromagnetics in India, and particularly in regard to noise sources due to power lines and so on. Also, I realised that the transient electromagnetic systems we had in those days were not suitable for looking for fractured rock aquifers in crystalline terrains, which cover a large part of the world where there is a desperate need for shallow groundwater resources for regional or remote rural communities. Some 20-odd years later, Andrew, Duncan and I met together and we talked through this problem, and we thought that the electronics had advanced to a stage where we could build a system to get high-resolution electromagnetic data in the near surface in difficult areas where there was a lot of electromagnetic noise. And we started the development of what we call the loop system. It is we think it's a unique system. I noticed the Danes have copied it, but it's designed to measure in the near surface in the top 30 to 50 metres, but it's being used worldwide, and you can see pictures there of it being used in Finland, in Ghana, Australia and various other places. It can be used wherever the operators can walk, and it measures down 30 to 50 metres as you're walking. It is sampling at a very high rate, so it's 5 lakh samples per second as we're walking. This enables us to do a lot of noise rejection in real time of sources like VLF transmissions, radio transmissions, power line transmissions. We actually store all that data in the backpack as we're walking, so we can extract out the sources due to power lines or VLF, or we can reject them. Typically we operate it at 75 hertz, but we can operate it at a range of frequencies. There you can see the operators, transmitter and receiver walking over a graphite deposit in Western Australia. We've also used it underground, and it's a well-calibrated system, and it has a range of options. So full data series collection. It's got a very accurate GPS in it to enable us to know where we've been and be able to repeat surveys to do time-lapse studies if needed. Why are we measuring conductivity? And this is a diagram that everybody should understand. Basically, there are 6 orders of magnitude of conductivity. So it's a very useful parameter to measure. Over on the left, you can see the most conductive things are sulfides, but sulfides overlap with graphite and they overlap with salt water. And there is a lot of interpretation in the process needed to understand what your source of electromagnetic response is. We've used it in a whole range of applications. Originally, I was thought it would be a environmental groundwater system, but Australia has a very active mineral exploration environment, and so it was soon being used for mineral explorers because it could guide their geochemical sampling and provide an additional mapping tool to magnetics and gravity at very fast sampling rates. So what does TEM look like? So I'll start this animation in a moment, but after every pulse, you get this diffusion current that moves downwards and outwards in the ground. And so going from early time to late time, so early time, middle time, late time, you get this diffusing current that moves downwards through the ground, and you can measure that with the receiver. So we can build up a conductivity section of the Earth, and if we do enough lines, we can build up a 3D volume of the Earth. So I'm going to, I could give a range of examples where we've used it for groundwater, but I just thought for this presentation, I'd concentrate on a couple of applications where we've used it for mineral exploration. This is a copper deposit. It's not economic. It didn't prove to be economic. In Western Australia, there was some signs of a gossan on the near surface, and a company invited us to do some test surveys there. You can see it's in an agricultural area. It's actually in a wheat field in the southwest of Western Australia. In farming country, there's power lines, there's fences and various other things. And this is a grid of the X and Z components. So we're collecting X, Y and Z components of the secondary field as we're walking. And generally we only use the X and Z, but you can use them all together in some advanced interpretation. This is at channel 4, so it's at 9 microseconds after switch off of the primary field. So it's early time. And what we're seeing you can see up in this part of the survey, some geological features very clearly. And in the south part, we've got where a salt lake is developing, so extremely conductive area. If we go through to late time, this conductor here has persisted. It's showing up as a bedrock conductor, and there's a few traces of it along this geological unit. It was interesting in terms of mineral exploration. So, and looking at it in section, there it is coming up as a really nice late time anomaly. And you're looking at, I've got the crosshairs on the Z component, but also showing nicely on the other two components as well. This is raw data. The traverse is 500 metres long, and we're using 75 hertz. So windows 4 microseconds through to 2.5 milliseconds. This is not seeing very deep, but it's showing as a nice dipping conductor, dipping to the east. If we modelled that up using Maxwell software, and there you're seeing the model in which one's which. The model's in the blue, and the raw data is in the pink. And we got a good match for a dipping conductor, so using a plate model, and it was drilled, and it got several thin zones with chalcopyrite in them, nothing that was particularly economic. But it was the first real discovery we had using mineral exploration discovery using loop. Unfortunately, not economic. The next example I'm going to give you is totally different. This is the Webb's Console, high-grade silver, lead, zinc deposits in northern New South Wales, over in the east of Australia. And it'd been mined since the 1890s with sporadic mining over some 60 years, and it had been stopped because of difficulties and finding more mineralisation. Lode Resources, an Australian listed company, started looking again at this area because of the very high grades involved, and we're looking for some way to to explore for more mineralisation in this area. So they're late-stage vertical pipes intruded into fractures in a granite with lead, galena mineralisation with silver in it, dominant at surface, and grading to a zinc-dominated mineralisation at depth. So the range of minerals in it, from galena, sphalerite, marmotite, arsenopyrite, chalcopyrite, minor bismuth, and a little bit of gold. All the pipes are in the granite, and there's a surface weathering, and a lot of them were potentially concealed under cover. The example there is one of the old shafts I'm standing beside, but the lode resources thought there was high potential for other pipes in the area. So they did some very detailed drone magnetics, which you can see on the left there, and that's got a tilt derivative filter on it, looking for some sort of control on the mineralisation. They really couldn't see it in the magnetics. All those little markers are things where there was indications of mineralisation, all those black and yellow squares. And so they then went back and did detailed gravity, and again didn't find any structural control they were looking for. That's when Keith Mays, one of the directors, called me up and asked whether he thought we could do it. So I went up and helped conduct this survey a couple of years ago. And what we got in the very early time, this is channel 1, it's 4 microseconds after turn-off on the left, is we're seeing some controls that seem to fit much better with the mineralisation than could be seen in either the magnetics or the gravity. On the right is the survey lines. It was very difficult terrain, very rocky, and a lot of very heavy vegetation. And we could only, in this case, manage 6.5 kilometres a day, which is really bad production rates for the loop system. We normally expect more than 15 kilometres a day, and in some cases up to 25 kilometres. So that looked really good, and Keith played with some better imaging, and sometimes it is much better to present this stuff in grayscale. And in the grayscale you can see these longitudinal structures, these ones here, which seem to be a control for the mineralisation. These are joints parallel to the granite margin where there's been deeper weathering, and the deepest weathering appeared to be where there was potential mineralisation, and the top of these pipes, being galena rich, had weathered slightly differently and deeper than the surrounding granite. So there was some new targets in there that Lode decided to follow up, and this is out of one of their stock exchange releases, that new targets that they'd found using the loop system, and then they proceeded to drill those, diamond drill, and came up with a resource estimation. You can see the drill holes there. This is a volume produced in Leapfrog software showing the mineralisation that was intersected in these new pipes. So interesting in that all we were really detecting here is the very tops of these pipes, but there was no other technique that was really working. Not even the geochemistry wasn't working for them here either. So a great discovery for the loop system. We've done some trials in Rajasthan in the last week, just trying it out. And this is a a little survey we did early on Sunday, and we have a little bedrock conductor here. It's not a great conductor. It's it's fairly weak, but it's showing a bedrock unit there that's more conductive than the surrounding medium. This over here is we're walking through a village and getting a response off the some of the very heavy iron gates there. But that's a nice bedrock conductor, slightly more conductive than the surrounding area. You can see it there in the profiles. It's about 250 metres wide, so it's some sort of looks like a vertically dipping geological unit. We haven't done any more modelling than that. I just thought it'd be a good thing to show, given that we've collected it this week. And another example where we've got although the colours are the same, this is an even weaker conductor here, one there and one there. This one we've done a couple lines. It's about, we did the first line twice at 2 different frequencies, but they match pretty well. Yeah, this is my last slide. Yeah, and it's showing a couple of units there that are moderately more conductive than the surrounding medium, but not. I don't think they're mineralisation. Thank you.
Any questions, please? This work you have done for GSI?
Yeah, GSI was that last one, yeah.
No, 5 kilometers north of Jaipur. 5 kilometers near Jaipur.
Yeah.
Near Jaipur. They are testing their instrument, or they have given some rope to them?
Have you able to correlate your data with the geology or the mineralization of that area?
In the GSI case?
Yeah.
I only did it on Monday. I haven't had time to do that. You haven't given me the data yet, so give us a break, will you? This system is designed to see probably to a maximum of 50 metres. It's designed to collect really high resolution 50 metres.
Just 50 meters?
Yes.
I don't feel it will work for us for once in everyone. Mineral exploration they have mentioned in the
The fact is that you cannot collect deeper information while you're walking. This is a system that is designed to be used in real time, in motion. You're not going to collect deeper information while you're walking. It is designed to collect very high resolution data in that top 50 metres. It's taking a reading every 1 to 2 metres as you're walking.
Okay, thank you. If not more questions, please join me giving a big hand to Dr. Street. So friends, we are moving to the last paper. Very long title, but integrated geophysical survey in Rajasthan by Nivedita. Yeah, please.
इसमें डाल दिया क्या पेन पीपीटी कौन सा है
अच्छा Very good evening to everyone. I am presenting the
integrated approach for mineral exploration that is having geophysical and geological integration, and then signature of mineralization in Nagaur, Sikar and Didwana, Kuchaman district of Rajasthan. If you If you look at the geological map of Rajasthan, we can see this blue. This cursor है, ये सही नहीं काम कर रहा। भाग रहा है।
इस पे देख के चलाओगे ना तो वो उल्टे करता है।
अच्छा।
इधर ही ऐसा लगेगा वहीं शो करेगा।
Okay. Now have a look in the overall geological map of Rajasthan. So we can see that where my pointer is pointing, this entire area is covered by Delhi meta sediments, and beyond to that we have a Trans Aravalli, and that area is entirely covered terrain, and the cover is ranging from 100 meter to 200 meter. And if you look at the geological map of this area, study area, you can see the entire area is shown by yellow color, which means that entire area is covered by thick alluvium. But few outcrops are available. If you look at the cursor here in the north part of the study area, that is belong to the Delhi meta sediments. Similarly, we have some outcrop in the southern part of area, and that meta sediments is also belong to the Delhi meta sediment. Beside that, we have a very limited outcrop on this center part of the study area, and also in the western part of the study area that belongs to the Marwar group of rocks, that is sedimentary rocks, consisting of both sandstone and limestone. Now, if you look at the Google imagery of this area is very important because Degana is situated in the center part here, and our study area is shown by the black color block. So Degana is situated, which is known for tungsten mineralization, and if we go in the south, Nadri is well known and established for lithium mineralization. Then we have a Balda tungsten mineralization, and if you go further in the northwest part of the area, we have Tosan, that is known for tungsten mineralization. But as we know, this is the Cretan boundary. So our exploration was not extensively planned in this area because the entire area is covered by thick alluvium. So now with the availability of geophysical data, now we have airborne geophysical data in this area, and we have gravity data also. So if you look at the regional map of aeromag data, even being a covered terrain, we have a very strong anomaly in the study area. I'm facing problem, sorry. अरे ये भाग जा रहा है ना.
इसमें देख के चलाओगे।
Okay.
तो वही काम करता है। ये पूरा मैप खोल रहा है।
Now if we focus at the geophysical anomaly, we can see we have a strong northeast trending lineaments in the gravity map, which is follow the trend of Delhi supergroup in the area. Beside that, we have also very strong northwest southeast trend of the magnetic anomaly, and these all magnetic anomalies meeting somewhere here and giving a very strong magnetic anomaly. If you look at the southern part where my cursor is there, Degana is situated within the gradient of aeromagnetic data. So, and similarly, in the western part, we are getting some circular magnetic anomaly within the low magnetic zone. So based on this data, since Degana is falling within the area and Tosam and Nadri Balda is coming in the same zone, we thought that this lineament, which is trending northeast, southwest, and northwest, southwest, and they are cutting across near the Khatu, so they may be potential for mineralization. So we have taken this area to understand the subsurface geology, and then if mineralization related to that one. Now, if you look at the RTP map, so I have shown here the magnetic anomaly derivative maps, and as well I have shown the gravity data also. If you look at the RTP map of aeromag data, we can see we are getting within this high magnetic zone, we are getting some still strong discrete magnetic anomalies. And in this part, we are getting a set of low magnetic and high magnetic, so there may be a structural discontinuity. We have validated this data, we will discuss in the later. When further we have processed this data, and we can see the similar feature we are getting in analytical signal also. And as we can see, the Degana is somewhere falling here within the magnetic gradient. From this reduced to pole, we can define this area in two segments. The eastern area is mostly defining the either low magnetic to moderate magnetic high, and the western part of the area is defined by high magnetic area. So there should be some lithological contrast. That's why we are getting such distinct magnetic anomaly. When we have a first derivative map also. So from this map, we were able to define some linear features. So we can easily see that how distinct this northwest-southeast linears as well as northeast tending southwest linear features has been properly defined. So these are nothing but the lineaments that has already been, that has also been validated in the ground. Now if we focus on the gravity map, in the gravity map also, this area has been divided in two zones. That is, this zone in the eastern side that is defined by low to moderate gravity, and further in the west, the area is defined by high gravity area. So there is some lithological contrast. But if you look at further in the first derivative map, the again area is defined very, very properly. So we are getting very low gravity, which is contributed by granites. We have validated. I will show you the photographs also. And this moderate gravity high within this zone either contributed by the granite or the metasediments, which are quite deeper in the depth. However, this strong gravity in the center is being contributed by the Marwar sediments. Generally, it is not usually happen. We are getting high magnetic, so it is unlike. But in the surface here, where my cursor is there, we are getting exposure of very thick multi-story sandstone. So probably we have initially we have interpreted this, there may be a sedimentary thick horizon, and these sandstone are ferruginous in nature, so probably these are being contributed from the sandstone. Similarly, if we look at the tilt derivative, and we have used for defining the contact and possibility of the lineaments. So if we look at this zone, which is highly sharp contact, and we are within this northwest southeast trending, this contact, we are also getting some trend which is cutting this, breaking the gravity high in this part. So probably these are some structures, and probably they may be very good for the mineralization point of view also. Here, Degana is again situated in this gradient. So these gradients and sharp difference between the high gravity and gravity low may be significant for the mineralization. Now, if you look at this gravity map of the area, then we have started validating that what may be the possibility of this gravity high and low. So we found that we are getting some serpentinite in the north of this area. But within this area, we are not getting up to 600 meter, we are only getting the sediments from the Marwars. Probably there is two possibility that this serpentinite either quite below the sedimentary cover, or the thickness of these sediments, Marwar sediments, are quite high compared to the granite. So we are, this gravity high is probably being contributed from that. Not only that, in the center part of this area, we have multi-story sandstone packages, which can be physically seen, and they are making a high hill around 200 meter above the surface. Now, as I discussed that we are getting some break in the gravity. We can see north, northwest, south trending this break in the gravity, and So probably these are the lineaments, and along these lineaments, as we can see, we are getting some groups and mafic dyes has been intruded along with this. So this confirms this. Yes, of course, the break is because of the lineament. If you look at this one, at this place, we are getting surface granite in the subsurface around 100 meter, but at the same time, south of this, we are getting granite at 200 meter. So it defines that there is substructural disturbances. Now, if we look at the area which we have already already told that there is a huge granitic plutons, and these are represented by 1, 2, 3, 4, 5, 6 like that. And similar granite has been collected from the duck bills. We have a beauty in the Rajasthan that we have a number of old duck bills which has been left because of low groundwater level. So we have collected all the samples from the granites, and we have classified also these granites. Probably this number 1 is classified as S-type granite, and in the Degana, north of Degana and surrounding in the Degana, we are getting mixed signature, that is A and S-type granite. We are also getting this the signature of I-type granite, which is mafic in nature. Similarly, when we have classified and we have done hydrogeochemistry also, so based on their nature of the granite, we are getting the chemical signature also. So within this I-type granite, we are getting the copper signatures, but in other granites which are S-type or A-type granite, we are not getting the copper. So as I said, that number of lineaments we have identified, because when we have taken the traverses, all the bells situated all along these lineaments, they have a quite good water quantity, as well as when we have recovered the granite, they have been traversed by number of pegmatites, quartz vein and calcite veins. So that indicate that, yes, of course, there is a possibility of the fracture system. Now we have tried to make the section also. So we have taken 3 profile line, AA, BB, and we have taken one more profile line so that this northwest-southeast trending lineaments can be defined from this. So if we take the gravity profile, as we go, start from here, you can see we have a very strong gravity high in the western portion. We have low gravity here in the center part, which is defined by granites, and again start rising up the gravity high in the eastern side. So if we start from here, as soon as we reach to this place, we are getting quite up notching here. So that defines that we have a gravity high. Similarly, as I said, there is a contact here, and here also there is a gravity gradient. 1 gravity gradient, 2 gravity gradient, and likely in the similar in the eastern side. Similarly, we are getting some Euler depth, and that is defining the deep fractures in the area. Similarly, in the profile line B, we are getting a similar pattern. When we have attempted this northwest, this section along the C and C dash, because in this area, the northwest-south trending lineaments are very important, because mafic dye has been placed along this, and we are getting all the mineralizations. Probably these are deep-seated fractures. We have brought out the mineralization acted as a pathways. So along this, as I said, even in these lineaments are quite clear in the 2D map, gravity map also. There is a break in the gravity, which I have already discussed in the first derivative maps. And we are getting similar in the Euler depth solution. So it is clear that, yes, of course, we are getting sharp contact. And one more important thing is that here we are getting granites, and here we are getting metasediment. So granite and metasediment cannot have a sharp contact, because granites are intrusive within the metasediment. So there is a possibility that there is some structural disturbances, or this granite and metasediment has a faulted contact. And based on this all interpretation, we have made a predictive geological map. So now we can see that this entire eastern part is covered by the granites. And of course, this is also covered by metasediments, which are either depicted by moderate to high gravity responses based on their depth location. If they are shallower, they are giving low gravity gradient. If the sediments are deeper, they are giving, if they are in shallow, they are giving strong gravity high. and if they are deeper, they are giving shallow gravity response. We have attempted this model, forward modeling also. So these are the parameters what we have used for this modeling. Now coming to the signature, as I said that the entire area has been covered by hydrogeochemical sampling because we do not have other options to do that. So based on this, we have recorded that this area is potential for copper, molybdenum, vanadium, and gold because we are getting graphite, and graphite is also having some copper mineralization. So all along this shear zone, we are defined the shear zone between the granite and metasediments. So we are getting copper value as well as we are giving having the graphite within the graphitic schist. This area which are predominantly covered by granites. So as I said, these granites are S-type granites. So we are getting copper, molybdenum, and tin mineralization. And this is the only granite where we have got tin signature in the hydrogeochemistry. So as I said that hydrogeochemical sampling and the digital footprinting is very important in the area which are fully covered to narrow down the area for further exploration. Similarly, in the north of Degana, we are getting signatures of tungsten, lithium, and cesium from, and we have done the drilling also. Similarly, in the eastern part, we are getting lithium signature in the hydrogeochemical, and we have punctured this area. I will show you the exploration data. If you look at this, what I was saying that I-type granite and this metasediments have is sharp contact, which is not possible in general. So even if you see the enlarged view of this, we can see that we have a very sharp gravity gradient between the granite and metasediments, which is also very well picked up in the magnetic data in the first derivative as well as in tilde derivative. And similarly, similar feature we are getting in from the Euler depth solution. When we have done detailed IP and SP survey, IP could not work because we have a graphitic cyst there, so it could not be possible. But similar features has been recorded in the SP data, and this define the shear zone. When we have drilled this area, we can see that we have intersected in 180 meters of graphitic system, which is also having a graphite. We have analyzed, and very encouraging results are there. If we look at the enlarged view of the core, we can see there is a fine foliation, and all along this foliation we have a graphitic cyst. We can see from this picture, graphites are quite prominent, as well as within the graphitic cyst we are getting some sulfide also. And these things can also be visualized from the petrographical studies. These fine lines, black, dark fine lines are nothing but a graphite. And within this cyst, we are getting some sulfide also, which has been also been recorded in the petrographical study here. As I said that this is shear zone. All along this, we have done two blocks here, and they have a similar result. So because of time constant, I am not showing that, but we can say this has also defined by the same studies. And we are getting HRE as well as LRE package, means granite has played an important role here. So there may be chance that this granite has a copper mineralization. But unfortunately, we have a very thick cover here. And the graphite has been proved by the XRD analysis as well as Raman study. Unfortunately, so far we are not having the carbon isotope to tell the nature of the graphite, whether they are magmatic or they are secondary origin. Similarly, as I said that this gravity data is very good. We have drilled here because if you look at this gravity data, we are getting low gravity, but within low gravity we are getting discrete aeromagnetic high. So this may be potential, and this aeromagnetic high is also trending northwest-southeast. So as I said, this northwest-southeast trending lineaments are very good. And we got some value of tungsten in the hydrogeochemical data. So we planned one borehole, and you can see 100-meter thick cover is there. And we intersected the granite, what we expected. We are getting a sequential medium to coarse grain granite applied, then UST is also we are getting highly fractured granite here. So that may be possibility of the mineralization. We could not hit the mineralization exactly, but we are within the system. We can see that we are getting the region also. So all these indications, we have fluorine data also from bedrock core samples. So we are getting high fluorine value. So it suggests that these granites are highly fractionated, and there is a possibility that we can get some mineralization in the surrounding if we go for detailed exploration. Similarly, in this area, as I said, all the low gravity is covered by the in the eastern side, either pegmatoidal granite or pegmatites. So we collected some chip sample from the dug wells, and we got some polylithionite. That is a variety of mica which also contain lithiums. And if you look at the hydrogeochemical samples, we are getting high value of lithium in this area. Even it goes up to 10,000 ppb. So we planned one borehole and we intersected what we predicted. We intersected the thick zone of pegmatite. Results are still awaited. So we are hoping for some critical mineralization in this part of the study area. Conclusion is that possibility of rare metal mineralization has also been indicated by the study of drill cores within the granite pegmatite on the eastern side of Degana and north of the study area beneath a thick soil cover. Encouraging results from these core samples would open new avenue for lithium, tungsten, and cesium exploration in the area. The study area lies in between the well-known rare metal mineralization at Tosam in the north and Balda and Nadri in the south. It is important to explore the area with further suitable semi-detailed geophysical surveys. Thank you, sir. Sir, there is two possibility because within the Marwar sediments, we are getting lignite basin also within the area. So either these gradients are because of some similar basins are developed there, or what we are suspecting the serpentinite, they may be at the base of the Marwar. So there is a possibility, but they are quite deeper. We are also getting the circular magnetic anomaly, and we collected the water sample, we collected the chip also, but I think we did not even get the signature of any mafic rock in the hydrogeochemistry as well as in the chip sample because they are quite deeper. So that is the beyond of our study. But in the first derivative, yes. So these are gradients. These are gradients only. See, sir, these are nothing but the gradients. See, there is a gradient. And within what I said, here you can look at the cursor. There is a lignite basin also. Within the Marwar, we are getting lignites. So probably such basins are existing there, or we have a deep fractures. Yes.
Royal extension.
Yes.
There are several blocks. They are small. They are doing very detailed work. You show the Google map. Yes, slides. Any big one further. आगे चलो. वो बीच का यहाँ ये लेवल है ठीक. देखिए, ये जो लिंक बना हुआ है ना आपका ये.
Yes, this one.
ये this link. I have seen AMD presentations. They are both very small identified. They have done electromagnetic as well as drilling, and they are to have uraniferous hematite zone they are getting, uraniferous sulfide they are getting. It is working in several blocks in this area. It's a Khatu Ringus area, na?
Yes.
Exactly, I remember this shape. I was part of the committee. Seeing this is very interesting. So, but every, I don't know, अभी data share करता है साहब? HOD साहब? MD data share करता है, हम लोगों को नहीं करता है? No, they don't share. दूसरे नहीं करते, हम तो बहुत पीछे लग रहे हैं, करो भाई, but they don't share. They don't share. I was in Central Region as well. It has been taken up to IS level. No, वो तो बहुत हो गया. But it is very big performance for sharing. But you see, they have done lot of detail work in this area. They are giving everything to everybody.
Sir, they might have done before, but for 3 years, 2022, we have not witnessed anyone. Oh, maybe, sir. Yes, sir. Yes, sir. Yes, sir. But this area is very potential because never been explored. Yes. Yes. Yes.
Still I say is untapped.
And
Lot of scope is there to work. We are integrated in that. Where I'm sure we'll have a vital breakthrough in there something.
And sir, I hope that this area is also potential for copper, because earlier we were suspecting that copper is secondary, but when we got the sulfur isotope, we are getting higher value. So that represent the magmatic. So either granites are mineralized, or somewhere in the shear zone the copper mineralization is there. Yes, sir. Yes, sir. But as we have collected data up to 500-600 feet, we did not, yes, further deeper.
I expected that GSI is a lot of, it's a good paper. Yeah, really, yes, it's a complete in totality. But further more work is settlement is required, it's my opinion.
Actually, yes. Yes, semi-detailed survey is required because from the regional data we cannot hit. Yes, yes. Yes. Yes, sir.
So please join me giving a big hand to Dr. Devi.
Thank you, sir. Thank you.
By 10-15 minutes because we started late. So this chairman, this session is not responsible for the delay. So thank you very much for all. Chair sir, please follow me.
So there is, it is
Thank you, sir, for your valuable remarks and words of wisdom. I now respectfully invite Shri Vijay V. Mughal, sir, Additional Director General, WR, to grace the stage and present the mementos to our esteemed chairperson, Dr. Dinesh Gupta, as a token of our appreciation and regard. Sir. Thank you, sir. Now I would like to request Dr. B.K. Nandi, Deputy Director General, to grace the stage and present mementos to our esteemed co-chairperson as a token of our appreciation and regards. As we conclude this session, we extend our heartfelt thanks to all speakers for their valuable contribution and to our chair and co-chair for steering the session with their expertise. We will now break for high tea and post the session and reassemble shortly for the next scheduled proceeding. Thank you everyone for your active participation.
Should I start? Good evening, everyone. I am Pritha Shet. I welcome you back on behalf of Geological Survey of India Western Region to the last session of this seminar. We will now start the 5th technical session titled Geophysical Insights Imaging the Earth. This session brings together the cutting-edge approaches that help us look beneath the Earth surface, literally through advanced geophysical tools, modeling techniques, and innovative subsurface imaging. It's my privilege to welcome our chair, Dr. B.K. Nandi, DDG Geophysics and NMH-1B GSI. Dr. Nandi is a senior geoscientist known for his leadership in geophysical mapping, national geoscience missions, and capacity building within the GSI. His extensive field and managerial experience continues to shape India's geophysical exploration strategies. I am equally privileged to have with us our co-chair, Sri Prakash Chaube, Director Geophysics Exploration. Sri Chaube brings decades of expertise in applied geoscience, especially in resource exploration and advanced survey techniques. His guidance has been pivotal in integrating modern geophysical workflows into exploration programs across diverse terrains. Our rapporteur for this session is Ms. Asna Siddiqui, Senior Geophysicist, GSIWR. Now, I request our esteemed chair and co-chair to take over proceedings of this session. The first presentation will be on the topic Enhanced 2D Geological Mapping from Gravity Data, Multi-Scale Derivatives and Probabilistic Classification by Shashank Narayan Verma and team.
So A very good evening to all. I am Shashank Narayan Verma, and the topic of my presentation is Enhanced 2D Geological Mapping from Gravity Data using a multi-scale derivative and probabilistic classification. I am the co-author of this abstract are Abhijit Nath, Sakir Sisodia, Sucheta Maurya, and Vinod sir. So moving forward, let us discuss the contents of this one. So I will briefly give the overview of the gravity data and its acquisition. After that, I'll discuss the algorithm that we have developed. Then I will show a synthetic test on the gravity data. Then I will show one case study, and then limitation and weakness of this algorithm. And finally, I will summarize my talk. So this is the simple CG6 instrument, and along with DGPS, that will be required to collect the gravity data sets with precise position. As we know that after the collection of the gravity data, applying all the corrections such as terrain correction, latitude, and elevation correction, we end up a Bouguer anomaly. So that Bouguer anomaly, we will be filtering to extract the features, and using a suitable inversion algorithm, we will be converting that data into density function, and that density function will be utilized to classify the rocks unit, like different rock units such as igneous, sedimentary, or metamorphic. So we have developed a Python-based program that computes the density function. Once we have the Bouguer anomaly, using that Bouguer anomaly, we will be using the simple Bouguer plate correction to estimate the density function of the subsurface geology, and using that geological density function, we will be correlating it with the different rock units, and that rock units will be used to interpret the subsurface lithology or geological situation of this area. So our code uses the first phase of this simple data cleaning. So our code is itself capable of handling the outlier. So it itself reduces any outlier present in the data set by using the statistical methods. Then we will be using that data set, clean data set, in a grid pattern after the interpolation. Then using the Bouguer plate section, we will be estimating the density function, and that density function we will be using to give the classification. For classification of the structure, here we are using the multiple derivatives such as tilt angle, analytical signal, along with the gradient. So all will be compositely used to identify the best possible structural feature of the lithology. And then we will be interpreting that. So over here, I am presenting a synthetic test. In the top left, I have prepared a spherical body that is somewhat lying over here and having a density contrast of 0.3. Then in this figure, I have a synthetic horizontal cylinder laid in a y direction. So that is having a density contrast of 0.1. Then we have this vertical cylinder that can simulate the presence of dike-like structure. So that is having a density of 0.1 gram per cc. And then we have this composite model, like adding all these anomaly and using this particular, this cursor is not working properly. Okay. So using this particular, we will be employing our prepared code to segregate like whether this particular code is working on the synthetic data set or not. So in this case, this is the simple Bouguer anomaly map and overlaid by the tilde derivative. Then here we have used the density function correlation. So you can observe our code has very well adopted the density function that we have given as an input. Like here you can see the high density lobe. This one is the low density horizontal cylinder that we have placed in the region. And over here, this vertical dike is also present. And based on that, this particular part actually utilizes the multi-derivative approach to demarcate the possible boundary. So you can see we are able to demarcate the possible structural boundary over here. So, and here our code itself provides a summarized overview of the different litho units based on the, like in the code itself, we have fed some of the density information. Based on that density information, it tries to estimate like what kind of rock it could be. Like as we know that same density could be approached by the multiple rocks. So here we are giving a probable range based on the density function estimates. So this is the one taste on the synthetic data sets. Similarly, we have employed this particular code on the gravity data set that of a topo sheet number 46F by 16. So this is the geological map of this region, and this is Bouguer anomaly collected over this region. So we have employed this algorithm. So here, the first figure shows the Bouguer anomaly along with the zero tilt. Here we have converted the density function using this particular algorithm. So you can see that our code has estimated the density function, and this one is roughly a sediment. In the geology itself, you can see the more or less the rocks are of sedimentary basin. And along with that, some basaltic intrusion is there. So basaltic intrusion might show the higher density values, whereas the sedimentary basin is having a lower density values. So our code has itself very much estimated the probable density functions. And when we compare like the results, like here we have this basaltic intrusion. Over here you can see the, so over here you can see that this particular region is showing some traces of this boundary. Along with that, this is the massive basaltic intrusion that we observed in the gravity data set. Here are some traces of the basalt also, but they are very much covered by the sands, sandstone, clay, shale, etc. So we have collected some of the rock sample also, and their density we have also estimated. So whatever the density estimates from the rock samples, they are very much correlating, like they are having a roughly error of 10% based on, because this algorithm is giving a average density structure, and when we have calculated the density from the rock sample, it is very much like correlating. So along with that, I have tested this particular algorithm on one more data set. Here, this is the data set of the Chitradurga. So here, this particular massive body is your metabasalt. So over this particular image is generated from the Voxy model that Geosoft is providing. So you can see that the structure that this metabasalt is having, this particular algorithm is very much capable of demarcating the probable boundary of this metabasalt region. So using this particular multi-derivative approach, we can very much estimate the density function along with the better structure of this particular region. Because we are, instead of relying on a single parameter, we are using multiple derivative approach. So like our code is very well automated. Like once you set the parameter, it will calculate all the stuffs in a single click. So it can detect the outliers. Along with that feature, it can extract density function. It can also estimate. Then based on those density functions, it can estimate what kind of probable rock types will be there. The cons of this one, like we have used a very simplistic horizontal slab model. So whenever we are having a very complex geological structure, so the density function estimates are not very much accurate. However, the structure that it estimates, it's very much correlating, like as we have seen in the case of Chitradurga. And like the same density function could be provided by multiple rock lithology, like the same density estimate could be of sandstone along with the granite also. So over there, this particular algorithm has a lacuna. And this one is like a rock, that like we have described the rock, what kind of rock type it could be. So it broadly classifies, not exactly. So that are the limitation. So in a nutshell, we provide a fully automated code that converts the density Boolean anomaly into density function. Also, it extracts the features like the structural boundary of this particular region, and it classifies the rock unit into different litho units, and it prepares a very high resolution output image. So thank you for your attention, and any questions? Yes, sir. Yes, sir, we have converted that topo sheet we have converted for better distance estimates. We are not keeping it in a lat long itself. We will be converting it into a distance. Yes, sir, we can reconvert that lat long position into spatial lat long. Like distance can be reconverted into a lat long itself. But for the calculation purposes, like we have to estimate the distance. So that distance we have to, this particular function will give a better estimate of the distance. Yeah. Sorry? Cell size, like it is NGPM map, so 2.5, like whatever the conventionals, 1.5 kilometer, the same we have kept it.
We are using GeoSAP,
Yes, sir.
Interpret, and other software, drone software.
Yes, sir.
For modeling, and how it is different from this software?
So one basic thing is like GeoSoft is a paid version, but our is like a Python based freely. So even someone is not having just a Python based module, they can simply use this code and in a single click. And again, the results are very much matching. You can see this one is from the GeoSoft, and this one is from our code estimated. So at least structural boundary, it can precisely demarcate. So one advantage is like we can have it like GSI can itself, yes, a free version of this. Yes, sir, the same results. And also like this is a algorithm, so we can have some add-ons, like we can incorporate the well log information and other information for better density correction, and we can have the structural control also. Like when we have a well log information, then we have the better estimates of the depth section, so that we can also incorporate in this particular algorithm, so it can better formulate the subsurface lithology. Sorry? Gravity only. No, sir. Yes, sir. The same way, like we have the formula, we know the theory, we can employ the same method. We can also perform the joint inversion also.
If there is no question, I have one to ask.
Yes, sir.
That with density distribution and gravity anomaly, you can have numerous density distribution to have the same anomaly.
Yes, sir. That is the yes, sir. That is the ambiguity of this.
How you are addressing that?
So this particular thing, like we are collecting also rock samples. The density information that we get from those rock samples, if they are correlating with our density estimates, then we are very much on the right track.
That's not, I am getting the surface distribution from density. What about the surface? How far I am going?
Like this will tell us, like what here we are assuming a simple thin like slab. So whatever the thickness of that slab, we are putting over here. So that slab is going to have the density. So this particular density estimates goes down to a depth of 1 kilometer. So this particular lithology.
You are assuming that my anomaly is within that 1 kilometer.
Yes, sir.
It's not, it has no contribution below that.
No, sir. Like it has.
There is a problem. There is
Yeah.
a inherent problem in gravity.
Yes, sir. Gravity method.
No doubt about it, but this is what you have represented is a very good attempt for your part, for GSI part, because if you go to the GeoSoft also, there is no scope of me inverting the data.
One thing we can also.
In GeoSoft, there is no inversion, even not a magnetic inversion. There is no inversion at all. The inversion scheme is not there. You have developed it. That's very good attempt. But you have to look into those things not only with the magnetic gravity. You have to incorporate gravity. You have to incorporate, say, if it's closed grid survey, resistivity, so that you can you have a control.
Yes, sir. Structural control.
Different data, so that your distribution of density, distribution of contrast, they will merge together, give you a near
Close.
near close out of global solutions. You will get some
Yes, sir.
optimum solution, some optimum solution. So this is good.
Yes, sir. Yes, sir. Thank you, sir.
So first of all, I would like to thank you for giving me the opportunity to talk to you today. So yes, my paper is sort of how we have to deal as geophysicists in the big world and through a geological survey. My talk is made with other co-authors, and you can see Johan Thury, Anne Bialkowski, and Gaëtan Lefebvre. They are all of them. They are from the BRGM, which is the French Geological Survey. I spent myself more than 20 years over there, and I was my last position was director of the science. So it's why I know very well what has been done and what is going on today. And now I move to Iris Instrument, which is a subsidiary of the BRGM, and we are innovated in geophysics in order to help the BRGM also, but all the customer in order to go to the forefront of the innovation and to tackle the challenge we have. Okay, we all have very, very big challenge. I just want to come back to critical raw mineral demand because as you know, we have the transition, energy transition, but also the digital transition. We all have smartphone, we need electricity for that, we need data center. So all of that we need copper, cobalt, lithium, gold, even silver. So lithium for sure. And so you see it, so we have to manage with that. And when you look at this, yes. When you look at this graph, it's really interesting. So it's short. So this person, this professor, made a very huge synthesis. So he's Australian, and you can see that he just gathered the data from 1900 down to 2020. And what you can see is the numbers of discoveries that has been done in the world. Okay, and what we can see is that in 2010 we were about 200 discovery per year, but today we have a big shrinking, and it's more 70 per year. And even nowadays, it's even less, okay, after 2020. So we face a very big challenge because we need more commodities than ever, and we do not discover the new big first big discovery, and this is very difficult. So what happens is up to 2020, we let the juniors company, so small players, in order to discover things, but they were lack of funding. And so now all of us, as nation, so we face very big trouble because we need these commodities. So the government themselves, they ask to the geological survey. It's the case in France, it's the case in many geological survey in Europe, it's the case here in India. So they ask us, as geological survey, to discover, okay, a new generation of things, and very quick, and that's our challenge. So the BRGM has had this commitment in February 2015, so the Minister of Energy and Mines, so came, and he said, okay, we give you 50 million euro, could be huge, so it's 50 million euro. In 5 years, you have to know where you have big discoveries, or even so ancient discoveries, but you have to review completely because so the metallogenic system are completely different, and you have to find so almost 10 new discovery in 5 years. So it's really a huge thing, and 4 of them so are in the metropolitan, so France, and one of them, so on the right here, this is in French Guiana, so it's near Brazil. Yes, so it's not only a question of discovering and having data, it's also now, as we did have, so with the plate tectonics so in the 70s, in between two all and now, so we have an adoption of the mineral system approach. It makes a big difference in order to understand what we are looking. So that means for geophysics, we have to take that in mind. We have geological objects in 3D, very much complicated, so with a source and a trap, with circulation of fluids, so paleofluids, along faults, structural control for magnesium. Then we have alteration, then we have weathering, then we have other sort of metallogenic system. So that means it's really not easy, and we cannot cover all our country. France is very small compared to India, so believe me, you are very 10 times more bigger than us. So, but we cannot cover everywhere. So we have to be clever. We have to be smart. We need an approach to just joining geology, geochemistry, geophysics, and we need really an integrative approach. So what did the BRGM? So when you look at here, the BRGM said, okay, we do have many data as yours, geological data, geophysical data. So all these data are in a depository, so and very well so organized. But we have to deal now with the new generation of innovation in order to cross this information. And so we cross all this information in order to do predictive map. So per commodities, for example, okay, predictive map of lithium, predictive map of cobalt, copper. So this is a big challenge, copper, for the today and for the year after, because of the electrification specifically. And you have the exploration, but today the exploration, it's 2 to 20 years sometime, okay? Could spend a lot of time. So we have new technique. So we talk about AEM, airborne. We will talk about so new generation of techniques, so developed by Iris Instrument, but we have to shorten this period, and we have also to shorten the exploitation and the time to have this exploitation. But it's more difficult to shorten this because so you have all the permitting and the discussion with citizens, so it could be very complicated. So here the challenge is to find new discovery, but also to revisit our geological system in the light of our better understanding. I come back again to short data because it's very interesting. What is said? Okay, we are the prospect scale and project scale. So strategic scale, okay, and tactics scale. So when we began to have, you are in greenfield, and then you see per depth, you want to find something. So basically, after 100 meters for the project scale, the thing is that in red you have the geophysics, here in pink, this is the knowledge of geology, and what we can see is that after 100 meters, nobody believe in geophysics. It's really, it's a challenge for geophysicists, okay? We do not trust us, okay? And this is the same, so for the tacti scale. After 200 meters, nobody trusts us. We have to change that paradigm. So it's very important for us to really propose advanced geophysics for that. It's why, so iris instruments for the BRGM itself, because so now they use, this is a picture of the BRGM, so doing the survey on one of the 4 or 5 zone currently in France. And what we have to do is image in 3D in order to image the system, the complicated system, geological system, I mean. We have to do something almost, for us, it was 1 kilometer depth. You can have an idea deeper, but you need the resolution 1 kilometer depth. It's really important to have information, so with a good resolution and in that depth. We have to diverse the resolution as well, and easy to use, and also suitable for complex things. Just a few words about what we call the full waiver system. If you are aware of what has been done, so in seismic, before seismic we did it 2-line, okay, and then after that some equipment arrived, and these were nodal equipment in order to spread these recorders. And then after that, you have a source. So for us, this is an electrical source. And so we inject, as it is traditionally for current, so for 2D ERT, a dipole of current. So here we have a remote electrodes. We have a motor generator. We have a transmitter. Transmitter, motor generators stay at the same place. And then you have another link here, another wire, but very simple wire, not a multi-core wire. And you inject in everywhere in the zone of interest where you already spread your small 2-channel recorders called full waiver. And then by injecting these all dipoles, so A, B, etc. So you inject and you eliminate underground, so with the current, and you register the variations of the voltage on 2 channels per box. What's this box? It's here, they are the black box for the recording, and you have also a red box just close to the transmitter in order to record the current. How we do that? How we merge all this data if there is no cable between the receivers? It's because we record everything in time series 10 to the GPS time synchronization. So every second we have the time from the satellite, and we have also an internal clock in order to adjust to have a better resolution inside the recorders. And we have, so this 2-channel system, 100 Hz sampling frequency for the recording of the voltage. There is no wire in between, so 2 boxes, 2 recorders. And you have the transmitter with this small box, the orange one, which just registers the current. You can use 1, 2, 3 transmitter. You can use any type of transmitter. If you have other transmitter, you can use it, okay? It's not a problem. And here for us, so we already developed several types of transmitter, but the higher power, so the powerful one, are TIP 12 kilowatt, it's 3,000 volts. And you can work together, you can plug 2 TIP 12, that means you will have 24,000 watts and 6,000 volts. So it's really a huge, if you can go deeper than 1 kilometer depth. And again, your result will be in full 3D, okay? It's not only the result that display in 3D. We record it in 3D. As a case history, so thank you to RC Geophysical. So one of our customers, they are in Peru, so they work in a very hilly area. So this mountain is 5,000 meters, so in altitude. So their survey are amazing. It's very difficult to work in this altitude, and it's really steepy. And they have a client, so Explo Andina. They already have a mine, this mine, and it's running. And they didn't want to stop the mining in order to have geophysical data. So it was really their challenge. So it's why they used ERT, electrical resistivity tomography, together with induced polarization. And the question was, can we expand the mine? Is it possible that we do have something else, so how the ore bodies is in this mountain underground? Can we invest in order to increase, to expand this mine? So it was the question. And this is a skarn. So a skarn, this is a feature very complicated, okay? This is deep-seated. This is, so here, it's controlled by a paleoorogeny, which is so just faults and inverse fault and thrust. And after that, you did have a transverse zone just moving the skarn, so again, so everything in control by two different orogenic systems, okay? And it's very deep, and you do not see, so here you do not have any outcrops because you have a weathering, even if we are very high altitude. So what they did, they did a 3D IP-induced polarization survey and ERT together, and they needed everything in 3D. And the mining was in activity, so again, it was a challenge considering the noise. So first of all, they said, okay, where can I set up my full waveform recorders? These are the black, where I do have to inject the dipole. These are the red dots. This is the dream, okay? His dream was that. But it was so much complicated and steepy and so on that when they did the permitting, okay, they said, we can inject here. And then you see that they have less injection point. However, they did have very good results, you will see. So this is the full waveform recording recording the voltage, and this is, so each injection point that has been done. And you can see that they didn't have too many people, so they did have about five people, so that means they spent 13 days. I did have with a team in Italy, so it was not in Italy, so in a volcano with an Italian team, so a volcano, so in the West Indies. I did in 3 days a very huge survey as well. So we were at the top of the volcano, and we worked only 1 day recording all the data, but we were 10 people on the field. So that means you have to arrange, so numbers of days, ratio, number of people. But here, so it took 13 days with almost 5 people. They made the 3D, so with a cubic, you will see that the data are 1 kilometer depth. And what is very interesting, so with 26 full wavers, they did have 142 transmission location. That means 142 dipole of injection. And then this is what they had, so in terms of resistivity. So you can see that you have features deeply seated, high conductive, and so they interpreted by the skarn itself is exactly what they were looking for, but they needed also to decipher it. It was very important to know where the chargeability was. And you see, this is the chargeability, 20 to 25 millivolt by volt. It's relatively important in this kind of geology. And so they said, okay, that means here we have high conductive and high chargeability anomaly. This is where the skarn, the mineralization in the skarn were. They knew that because they had information about the petrophysics, about the sampling and the geology with the mines. So they decided, so in their report, they recommend to Explore Andina to expand the mine in that area. It's what they did. And they started drilling, and they were very surprised because they did have a grade, very important, even more than in certain area here. And they were very happy to do not have, they didn't stop mining, okay, because it's really expensive if you stop the work activity. And they were able now, now they are in the process to open, this extension, so they have decided to do that. So thank you to RC Geophysical. We do have others, example, this one has been published. I can give you the publication. I can also give you other publications from others. This is an example, this one, for the mining exploration, but there is also example for deep aquifer. I say deep, okay, that means 100 meters. Below, it's better to use other type of equipment, okay? But for 3D modeling, for 3D information, for groundwater, or for mining exploration, you can really definitely use the full river because it provides you guarantees to go deep in ERT and also in induced polarization. And so it reduces the time to exploitation. It de-risks when you put, you decide to put your boreholes. And again, I'm a fervent defender of we have to merge the data. We have to be inclusive. We cannot select so we have to drill with only an information of geophysics, neither an information of geology. It's very important, and this is our duty as geological survey. We are the temple of all the data. So this is our duty to select and to say after that, okay, this zone are promising. And then after that, so whatever you can, depending about the governance, but in France typically, we will open auction, so for private sector, so it's the politic that the government followed. But anyhow, you need this information from the geological survey. So thanks to the geological survey of BRGM for giving me so this kind of a image. So they were on the field 2 weeks ago, so it was nice. It's why I was not able so to show you the information they get. And thank you very much.
Any question from the audience?
What I can add is that we are very open to do seminar online if you need. If you need any discussion or just presentation of what is possible, we have example from our customer. We have example from the BRGM as well. If you need any talk, seminar online, or even so, I used to come almost every 2 years, or even I can come next year, and I will be very, very, it will be very nice for me to explain that, because this is, as you say, it's something new. We cannot handle it in 5 minutes or even 10. So that means, yeah, we need to discuss, to help all the new generation of geophysicists in order to handle the 3D. Otherwise, we will have trouble to have the challenge.
You are claiming 1 kilometer depth. So, for 1 kilometer depth, what should be the length of the profile?
You're right. This is a very good question. So if you want, for example, depending the geology, it's why I don't like, in this example, they reach 1 kilometer depth, and the farthest electrodes were 3 kilometers far away, a third. Okay, this is a sort of pole-dipole configuration. Okay, even if you can do whatever type of configuration, it's a sort of, so to reach 1 kilometer depth, if you are in good, they were in good condition, but they did have very high conductive mineralization. So that means they lose a lot of signal, okay, of electrical signal. But you see, 3 kilometers, a band of 3 kilometers allows you to have in the center 1 kilometer depth. But after that, more than 1 kilometer, today we have some customers who deal with 150 kilowatts of transmission. Yeah, it's very, very impressive. It's Ivanhoe Electric, so they are in Middle East, in Saudi Arabia. So they work with our full river. they claim to get 2 kilometers. But for me, it's very important that to understand that magnetotelluric give you deeper information, but you don't have the resolution. But having magnetotelluric plus ERT, 3D ERT, and IP give you a good information because we need the resolution down to 1 kilometer depth. And even this resolution helps to model, to invert the magnetotelluric data. So I don't want to confront the geophysical method because all can help, we can help together. This is a real key. So again, it depends about the case study. So here, they had really good information down to 1 kilometer depth with this configuration. They had 10 kilowatts for the transmitter. When we work, so again, I work on Volcano. It was a very difficult zone, and we were so with 3 kilowatts, we have very good data down to 400 meters. Why I'm sure that the data were good is because we made a matrix of sensitivity. So we knew exactly where we could trace our data. And for the 3D modeling, here they use GeoSoft, but now so this customer use REST 3D as well, or ERT Lab. So you have now many 3D inversion software that allow you to handle to invert, but also allow you to know if you can trust your data in a certain depth. Because I understand completely your point. It's very difficult. We cannot claim that we go down to 1 kilometer or 2 kilometers if we have just three data. You see what I mean? So we need to be sure. And so for that, it exists now the matrix of sensitivity in order to having, so you can do synthetic first before going on the field. And then after that, you can have the matrix of sensitivity when you say, okay, after this depth, I cannot trust my model, okay? The inversion, so it's not good. So it's not good. I cannot rely on it.
Any other question from any side? Hello. If no question, I have one thing to ask. You say there are many nodes. What is the minimum number of nodes we need so that we can do this work? Minimum number of nodes. So there are many nodes, as you said, though it is wireless. So 25 by 25, say 5 by 5 array. That also need 25 nodes.
For 1 cubic kilometer, so for a zone, so a square kilometer on the surface, we say the best is to have 20 nodes, okay? 20 nodes, and then after that, for the resolution, you adjust the length of the dipole, of the VMN dipole. And if you don't have 20 because you cannot afford for 20, whatever, we have many customers who did that. They purchase 10, and then you have to move the nodes. Otherwise, after that, you can just increase the number of nodes. But 20, it's a good number to have 1 square kilometer on the surface.
With 20 nodes, we cannot cover 1 kilometer, 1 square kilometer at a time.
Yeah.
So we have to divide it in different sector and do it.
He made, so the guy here, he made, so with, you see, they had 26 because he wanted to put more, but he made, this is, because it's not a real square, it's a rectangle, but if he had only 20 nodes, he will have done 1 kilometer and 1 kilometer, but here it's a little bit more. He used to work, so this customer used to work only with 20 nodes by 20 nodes, and he made 1 square kilometers. So it's why it's a really, So it's what we recommend. 20 full waiver for 1 square kilometer on the surface.
Finally, I want to know what is the drawback, what is the negative. Any system has some
What is the drawback compared to another? It's not, you are obliged to be on the, to have a contact with the soil. You cannot do with airborne or with drone, for example. The drawback of the full waiver system compared to traditional is that, okay, you will deal with minimum 15 meter of dipole VMN. If you want a very high resolution for the 51st meter, do not use this. Okay, it's better to use traditional, multi-wire cable, in order to have 5 meter or 10 meter or whatever, even 2 meter if you want very shallow. So don't use this if you need a good resolution in the first 50 meters. It's not suitable for that. Use other things.
The next one,
The last one, sir.
nuclear magnetic resonance technology
Yes, sir.
as direct mineral indicated, risking the exploration, a unique technology. By will be presented. There are many authors.
Yes, sir. Yes, sir.
Subhasis said. Okay, there are many authors.
Yes, sir.
As many as five. Subhasis said.
Can I start?
Okay.
Good evening, everybody. My name is Subhasis Seth, and I am here today to discuss a transformative approach to mineral exploration. The title of my talk is Nuclear Magnetic Resonance Technology as Direct Mineral Indicator Tool, which focusing on its fundamentally de-risking the exploration process. For decades, the traditional process of exploration has been defined by 3 challenges. It's high cost, time consuming, and high risk. But what RSNMR technology, in short, the NMR technology we are talking, in short we call it RSNMR technology. So what it offers a time and cost efficiency, it offers enhanced precision, and it offers a reduced exploration risk. So what is the science behind this technology? So fundamentally, the science behind this technology is the nuclear magnetic resonance, or the NMR technology. The principle of this technology is the nuclei of every element exhibits a characteristic NMR spectra in presence of any external magnetic field. So in RSNMR technology, we consider Earth's magnetic field as the external magnetic field. So what happens in the Earth's subsurface, when there are elements or any mineral we are looking for, the nuclei of a particular element in presence of Earth's magnetic field goes to excited state and comes down. During this process, it emits the NMR spectra. And when a satellite recording multispectral, full, like from ultraviolet to infrared, full band analog imagery over this surface, these NMR spectra emitted by these nuclei is being recorded. Now, our technology, so the data is being recorded in the satellite analog imageries. Now we need a technology to discover or identify these spectra which have been recorded on the imageries. So we have developed a technology called the POISE technology, which includes it's a patented technology by Sevastopol State University, Russia. So what it has developed a technology or instrument or a process which will be able to identify or detect these NMR spectra over a satellite imagery, analog satellite imageries. So how we implement this technology? So this technology is implemented in two stages, stage 1 and stage 2. So stage 1 is a remote analysis where we do the processing and analysis of the analog satellite imageries, and stage 2 is the field verification. The through stage 1 we get the accuracy of up to 60 to 85%, whereas if we want to go for the field verification, the accuracy goes up to 90 to 95%. So stage 1 is a laboratory-based analysis where we process the satellite imageries with specially created nanogels through a specialized instrument called the POISC instrument and a small-scale nuclear reactor. And in stage 2, it's in field, we mobilize the mobile POISC equipment to the field. We acquire data at certain desired points, and then we calculate the depth and the extent of the mineral deposits. So how it works? So stage 1 is further subdivided into two stages, step 1 and step 2. So step 1 is the sample analysis and the data preparation stage, where, so based on this, we will require a small sample from the field. And I'm sure that when we go for a geological area mapping or anything, we get the samples based on which we determine that whether there is a possibility of mineralization at that place or not. So we need the sample, we analyze the sample, and we identify some reference elements in this sample, which we have to identify, or target elements, which we are going to find out in the satellite imageries. So we do this we do the sample analysis using neutron activation method, atomic absorption, and Van Gogh fluorescence method. We identify the reference elements, and then we calibrate our POISC equipment based on the elements we are looking forward to or we are searching for. We do the laboratory testing of the samples through the POISC equipment. We test the calibration of the POISC equipment from where we have collected the samples on those places. Once that the test is successful, we do the process of the next step. I will further explain. And based on the reference elements which I have identified through the sample analysis, or step 1, sample analysis, we prepare some nanogels and some chemicals which contains the nanoparticles of these reference elements within that solutions. So what in step 2, what we do, so we generally procure the hyperspectral, multispectral analog imageries and digital imageries from different satellite agencies based on our target element and based on the requirement of the project. We treat these satellite imageries with the prepared these nanogels and the chemicals which we have prepared during our step 1 stage, and then we process these treated satellite imageries within a small-scale nuclear reactor. Within the small-scale nuclear reactor, we create the environment of Earth's magnetic field. What happens? So these satellite imageries have the data or recorded, the NMR spectra recorded in it. Now, when we treat these imageries with the nanogels and the chemicals, which has the nanoparticles of the reference elements, in the presence within the nuclear reactor, when we create the artificial magnetic field, so these nanoparticles which are there in the nanogels, they create the same effect of the NMR spectra. When it resonates with the NMR spectra which has been recorded in the imagery, we get bright spots. So in this figure we can see, so once we get these bright spots, we can map these bright spots on the analog imageries. And once we map it, and then we transfer these mapped analog images, these prospects on a digital map. And at the end, we deliver the boundaries of the identified anomaly areas. We contour the mineral accumulation, and we determine the depth. We identify the depth of the mineral accumulation. So in this process, we use the full spectrum of the electromagnetic waves. So we start from the infrared segment up to the ultraviolet frequency range. So, and this is the imagery of the POISC equipment, which is the only one kind in the world. There is no second POISC equipment. These are the samples of the test plates. So these are the plates where the analog imageries have been treated with the specific kind of chemicals and nanogels and ready to get inside the nuclear reactor. And this is the nuclear reactor which we use. So this nuclear reactor is present in the Sevastopol State University. So in Europe, only one university has this small-scale nuclear reactor. So the very important point is how we determine the depth of the occurrence. So we can aerially map where is the prospect identified through the NMR spectrum, where we get the bright spots and everything, mapping the bright spots, but how we determine the depth of this prospect or the minerals. So what happens, so if suppose there is a prospect or deposit at this depth, so to determine the depth, we consider data from two satellites, which are at two different angles. We have acquired the data at the same place from two different angles and two different heights. So when we procure the data from the satellite agencies, they provide us at what depth, at what height the satellite was there when it was recording the data, and at what angle it has taken the data. So when we compare the two satellite data, if there is an object here, for a satellite which is just above the prospect, we will get the signal just over the prospect. Whereas a satellite which is at a different angle, at a different height, there will be a shift in the signal. So we can easily measure this shift. We know the angle at which the satellites have taken the imageries, and we can, through using the triangulation method, we can easily calculate the depth of the prospect using this formula. So stage 2, which is a field study, this is we call the confirmation study. So it is a optional one. So till stage 1, we get conformity up to 85%, accuracy up to 85%. If client wants, they want to have a better accuracy, so we can go for the field study. So in field study, what we do, we have a mobile POISC equipment. You can see here, this is the equipment, very small, 50 kilograms of a weight. So we, based on the results from the stage 1 study, the interest zone which we identify, along the interest zone, in discussion with the client, we make profiles where we want to and determine the data points at exactly which points we have to record or measure the data, or record the data, process it, and interpret it. Now, what it does in field. So this POISC, specially created POISC equipment, it has a injector or generator which creates a particular, which creates the frequency, electromagnetic frequency of a particular frequency, and a receiver which records that frequency, reflected when it comes reflected. Now what we do, when we are looking for an element, suppose we are looking for a copper, so copper has a specific NMR frequency spectra in presence of Earth's magnetic field. So we know what spectra or at what frequency this copper nuclei will resonate with the induced EM field. So we calibrate the generator in such a way so that it only induces the EM energy at that particular frequency, which goes there. If there is a copper body, it modulates, it resonates, and then the energy reflects back and the receiver records. Through this, we can calculate the accurate depth of the prospect in a particular point. So this is a flowchart for this. It's like in stage 2, we do first planning and designing, which is based on the stage 1 results. We mobilize the POISC equipment. We acquire the data at desired field locations, field points. We process and interpret the acquired data, determine the depth of and the horizon measurements, and we submit a report which gives you the boundaries of the identified anomalous areas, contours of mineral accumulation, and depth determination of the mineral deposit. So, what deliverables we give in our after study? So, stage 1, which gives the accuracy of up to 60 to 85%. We provide maps with identified anomalies associated with target mineral accumulation, cross-sections with depth of occurrence, recommendations where drill for further exploration purpose, recommendation for field study, and for time duration, it's like for about 1,000 square kilometer of area, we need 3 months of time to do the job. Whereas for stage 2, which gives accuracy up to 90 to 95%, the deliverables will be more same, but the accuracy level is high. So maps with more precise and delineated areas, cross-sections with more precise depths, thickness of the potential deposit, and time duration is depend on how many field data we're going to acquire or record. It depends on the result of the stage 1. So till now, we have completed more than 380 projects globally, which includes the oil and gas, mineral deposit, groundwater, geothermal, which can do all the, so moreover, we have done projects in all over the world. So I have, because of time, I am going to present only 3 case studies, which are very recent ones. So this is a case study from China for lithium. So case study in India we have done in oil and gas industry, not in mineral yet. Oil and gas for ONGC. Yes, sir? Okay, sir. So very small. So this is a case study from China for the lithium discovery. So I think you might have heard of the latest lithium, one of the biggest lithium deposits in China they have discovered. So this is the map. So here it was given like this, yellow is the boundary, and they wanted to understand whether there is a lithium deposit or not. So they have performed this RSNMR stage 1 study only. They have not gone for the stage 2 study. And this, through this, after doing the RSNMR study, we have identified this. These are the prospective areas for lithium deposits. In further, they have done other geophysical activities in these focused these areas, and then they have, and we provide also the vertical map, 2D maps, where we have designed over a profile like this is the deposit looks like. So another case study is again from China. It is for gold exploration. So this is the map which is showing the bright spots after this RSNMR thing. We mapped this bright spots and transferred them to digital maps, and these are the small prospects, 3 prospects. So out of these 3 we have, this mouse is crazy, yeah. So this prospect, we have made a profile along this thing, and we have calculated the depth of occurrence of gold accumulation over 3 points, and then extrapolated. And along with this, we have also provided the tectonic fault map in that area.
I think that's fine.
So there is another case study. So this is a case study from Peru, copper. So this is a mining belt. It was under exploitation. The company wanted to know that whether they want to continue the mining or they should shut down. So before deciding, taking a decision, they did the RSNMR study, stage 1 study, and then they find out that there are much more deeper deposits, and so they continued mining in the area. So points to consider, the technology is highly cost.
I think it is over. We understood the things.
Okay. So
in
thank you.
India, you have done for oil.
ONGC, sir.
ONGC. What is the outcome?
Results are good, but because of the confidentiality, we have not yet got the permission to show the results, but reports are very good. So they are going to drill wells in next 3 months.
Okay, thank you. Now, I think there should be many questions from the house, because this is one of the cutting-edge technology. So, please come. No question. I have many questions regarding
Yes, sir.
this subject.
I'm ready to answer, sir.
But I think this time is limited. One thing you have told, you can find the date, but you have shown this is the anomaly. This is my object, and I will get the peak one. I will get the second peak, and from the angle I will find out the date. But how do you know this
Yes, sir. Yes, sir.
How do you know this is your ore body?
This is my?
This is your ore body, just above that you are recording.
No, this is a schematic diagram, sir, to make it understand. So basically what happens, sir, if suppose a ore body is there down and we are doing this anomaly mapping, so we are getting an anomaly map, but we are doing it from the satellite. So now we know at what angle satellite has taken the imagery at this. So it can,
Satellite is taking the same
same area image, same point.
What will be the difference in the signal? Will it be?
No, that's the thing, sir. There will be no difference in the signal. There will be shift in the signal. There will be shift in the signal. So we can measure the shift physically. We can measure the shift. So it's the same ore body in the same area. Two satellites taking recording the same data from for the same area. Now the signal. See, the object is at the one place. The object is not moving.
My question is, how do you come to know this is from zenith, just above the ore body?
No, it can be, sir. It can. This satellite can be here also.
Yes.
So that's what I'm saying. So I know, but if satellite is here, no, that's why it's satellite. But when at what angle this is taking? So satellite, when it acquires the data, it acquires in a particular angle.
Know the ore body. There will be many points. There are so many points regarding this. Let us.
No, sir. See.
I'll discuss it later on.
Okay, sir.
But this is. I hope this is a cutting edge technology which is introduced in India.
Yes, sir. We are trying.
And the result, we don't know.
No, sir. Internationally, it is proven, sir. And I don't think geology changes from country to country.
When we do in our country and we are confident to get some result and get something, so we develop more confidence on this subject. So okay, this presentation is very good, and I request all of you to back.
Thank you, sir.
Thank you.
It's the same procedure how the satellite gravity was taken, the gray satellites.
I am not getting it.
Actually, you can correct the satellite data using the gravity. Satellite gravity data using the satellite. So those satellite names are grays. Maybe the same procedure they will take.
No, it's a different. These are different satellites which only focuses on the analog imagery. So these are they acquires the data at full band of the EM data. So it is nothing to do. No, see, satellite when it goes above the area, it takes the pictures. So that's it records the data when it goes above the area. It's analog image. Don't get confused with the digital data. So it's not a digital data.
I feel that maybe based on observed data, we cannot able to say maybe we need to more process.
I'm not getting it.
Maybe by collecting the raw data with that mechanism, it's not able to reveal the structures in very properly.
So there is in this
Definitely we need to.
in this technology there is nothing, no raw data. You don't need to process the data. You don't need to
So what
interpret
is the
the
final
data.
output it was collecting?
Final output is just a minute. So if you have an area to explore, suppose 200 square kilometer.
No, sir, just output. What is the output? Whether
That's what I'm showing. This is the result output. So if this yellow is your area of interest, I will give you that these are the areas where you have lithium deposits. And this over one thing, we will calculate the depth for all the prospects.
No, sir,
So here I have shown.
my question is, suppose if we are taking the satellite gravity data, the output will be.
I'm not taking satellite gravity data.
Just I'm explaining. It is in the milligal or it is a aeromagnet, it is a nanotesla. So what is the data it is collecting?
EM.
EM.
Electromagnetic spectrum.
But like a spectrometry.
You can say, yeah, it's very close to like what you do in spectrometric analysis. Like you identify the elements, you go through the spectra, and then identify like this is what the mineral is.
Spectral peaks.
So it is like, but
not
here,
EM.
yes, but here the physical parameter is the NMR.
The spectral peaks.
Yeah, but here the parameter is NMR. That's the thing. Yeah.
Thank you, sir.
Thank you, sir.
To conclude this session, I would request our chair and co-chair to offer their valuable remarks on this session.
From last two sessions, we have seen the presentation on various applications of geophysics from near surface to deeper with conventional and state of the
Thank you, sir. We are extremely grateful to our chair, co-chair, rapporteur, and all distinguished speakers for making this session a success. Now, I would request Sri LMS Mora, Deputy Director General, Regional Mission Head 2, GSIWR, to kindly come forward and facilitate our chair and co-chair for their valuable contributions. Thank you, sir. Thank you, everyone. I would request everyone to join the closing ceremony, which will be held on main auditorium. Thank you.
आपका हो गया क्या ठीक है